as dimension of capabilities to control different chemical and other industrial processes. So the only limit is your imagination. Yet another motivation, which is not related to actually to the spectroscopy, is free space optical communications. Actually, what is good about mid-infrared, that the ray scattering is inverse proportional to wavelength in force power. So if you have your anti-fog headlights just shifted a little bit from green-white to red, orange-red, then imagine what happens if you shift by an order of magnitude from 0.8 micron, which is the edge of our vision, to 8 micron. So it is any fog, any smoke, rain, snow just are invisible in this range. So the whole capabilities to the domestic applications from roof to roof, you can develop your networks just in a matter of minutes or, well, half an hour or so. And this research is and applications are ongoing. So, but for this you need power, and our idea was to have high power laser diodes, quantum cascade lasers produced here totally in these borders. So we started from 4.5, which is the best developed wavelength range, and oops, a bit too loud. And actually, here you have some complications because of the energy of photon. You need typically these structures are grown from arsenides on indium phosphide substrates, and you have the options of having your heterostructures lattice matched to the substrate or mismatched with strain and stress compensated inside the structure. And so we choose this approach because this gives a deeper quantum well and less escape rate. Still, you see that our upper level lifetime is like 2.5, and the radiation transition time is 7.5. And this means that a lot of electrons just escape from the designed path and go to all directions except going to layers. And but still, the figure of merit is quite good, which is 9 picoseconds nanometer, and we were in strong belief that this structure will lace fine. And we made 15 repeats of these quantum cascades, and also we took some consideration about the cladding. You know, when you design the laser for this huge wavelength, you really need to think about the cladding, because the thicker it is, the less escape of the mode you experience, and you have less absorption in the contacts. But the thicker is this cladding, which is undoped, then the higher thermal resistance you put to your device, and so you put a heater next to your active region, which is not good for lasing. And the growth was done at industrial scale MBA machine Reber 49 at Connector Optics in St. Petersburg. And we process these structures into, well, a long story short, when we process this structure with double trenches, it appears that our approach to the cladding is almost useless, because, well, we have done well with cladding, but here in the trenches the mode leaks the metal, and we can do nothing about that. And so we just increased the number of cascades and to 30 and then to 45 and increase the power by more than the order of magnitude. Compared to the results of colleagues on the West, the group of Manish Razegi in Northwestern University produced a whooping 120 watts, the similar wavelength, but this is with 400 micron stripe. We had only 50 micron, and if you look here, she has the similar stripe here, and the power is very, very similar. So we are on good track. Then we go on to the 8 micron wavelength. So the photon is twice less fat, and we didn't need to deal with the lattice mismatched structures, and we used just lattice matched bands. And even with this simple approach, we produce the figure of merit 50% better than we had before. This was actually grown as well on the Rebel 49 machine, and also we did some efforts to put the mode lower into substrate. So we instead of having indium phosphide cladding, low cladding, we put the indium gallium arsenide one, so the mode shifted from the contacts a bit, and that helped us a lot. And also we played with cladding quite extensively. Here we put 3 different types of cladding grown by Musevidi at Polus in Moscow, and the difference was that either just step doped or gradient doped, and what is the contact, indium phosphide or indium gallium arsenide. All these types performed very well, and at the time of that research, this was a kind of record high power compared to what colleagues had in the West. But very interestingly, the highest power was achieved at the structure with the least efficiency, because it appears that our indium phosphide contact was not doped enough, and so we had high serial resistance at it, and that made our efficiency lower than we hoped for. So having these lessons, we have gone to the lattice mismatched structure at the 8 microns, and it was so much mismatched that we had to put the lattice matched, this is a pair, so this is the third one in this sequence, to take to compensate this mismatch and associate the strain. And comparing what we had in lattice matched and lattice mismatched immediately result in higher T0, the characteristic temperature. So it is got almost twice better. And the power was remarkably good. It's higher than 20 watts. And comparing to what we have in lattice mesh structure, we see that this some better cladding, better contact doping, and better efficiency results in less heat deposited into the structure. How we take these measurements? We do the time traces with the light going through the monochromator. So we put monochromator to a certain wavelength, then we take spectra, then we shift the wavelength, take spectra again, repeat this 500 times, and that's it. And this shows what is the chirp of this radiation. The higher chirp, the higher heating rate. So you see that the heating rate here difference quite remarkably by 30%. And if you think about what happens if you go from short pulse pumping to the continuous wave, then you immediately think about temperature gain. And obviously the results in the power in the continuous wave is much lower compared to the pulse. And you can trace actually how temperature is rising here. If you just increase the temperature of your heat sink, then the threshold goes up and efficiency going down. And if you put your laser into quasi-CME mode with pulses not as short as 100 nanoseconds but 100 microseconds, then you see as here that the power degrades. And taking the measurements of the degradation, you can estimate your temperature increase. And in our case, it is close to 100 Kelvin, which is quite remarkable and explains why the power in continuous wave is so low compared to the short pulsed. Well, and the most exciting to my taste here is the quantum cascade detectors, which we managed to produce from the same structures. I believe I have another 2 or maybe 1 minute. Yeah, okay. So we have done this in master-slave geometry just with lenses, but it can be easily done in kind of photonic chip. And why this is very good is that you can put the same couple of chips, big chip and small chip, on the same heat sink and have a power monitor. But this is very handy to the real world applications, so you can monitor your power. But what is more important is that this approach to the heterogeneous detection, because if you have some light coming from somewhere, from a star or from anywhere, you can detect it with this detector. This is not the best detector in the world, but here you detect the difference frequency. And for this difference frequency, please look here, the signal is the detectable signal, the proportional to the strength of local oscillator. So if you have high power laser on board, then you enhance your detection signal. So this is very good for many applications. So I go to conclusions. I will not read it to save time. Thank you so much for your attention. I am ready for your questions.
Thank you very much for for very interesting presentation. And now we have time for a couple of questions. Please.
Thank you for your nice talk. My question is about your temporal properties, because your spectrum is just a little bit spiky. Here it is, yes, for this slide. Yes, and what about the temporal characteristics? What about the temporal? And what do you have in time domain for your pulse?
Actually, this is time domain. So you start from this point, which is corresponding to short pulse pumping, and then it goes to some kind of degradation because of heating. So the heat is deposited. So as I shown here, your light current characteristic goes with heat. Where is emitter? Okay. So it goes at low temperatures here, at high temperatures here, and so this mimics what happens here. So you have higher temperature because of heat deposited with your pulse, and so it degrades the power.
Thank you. But can you imagine how to go to shorter pulses, not with so long pulses, maybe picosecond pulses or femtosecond pulses? Do you know some kind of a perspective
Okay, you mean just not the gain switch, but you mean mod local or something like that. Okay, you know, for passive mod locking in laser diodes, you have a saturable absorber, which is produced either by some ion bombardment or by reverse bias. Both of this approach doesn't work with quantum cascade lasers. So we believe that we have the absorption on the edges of the structure, I mean on the side edges. And this gives us nice combs produced in our lab, and we have published some results. I don't have this here, but we can discuss later. But we cannot actually, at these wavelengths, we cannot trace exactly what kind of pulses we have, because our detection is limited to 1 gigahertz at the moment. We believe that we have something faster in our system, but we cannot prove it yet. We will do.
Thank you. Okay, one more very short question.
What about long-term stability of your diodes?
Actually, this we studied this, and we put samples to the long-term degradation test, and one of them was just killed by a screwdriver after 1,000 hours, and the other one was just probably still alive. So we can well imagine that this is kind of thousands hours at real test, not temperature enhanced, but what it is exactly we don't know yet. So for lab grade it is perfectly okay. For industrial applications it still needs some better research.
Okay, thank you very much.
Thank
for
you.
your presentation.
Thank you. Thank you. Thank you.
The second talk will be done by Professor Bufetov. Oh, no, by Dr. Sveshkov.
Как его включить? С вопросом. My lecture is named Current Progress in Rare Earth Doped Chalcogenide Glass Lasers. This investigation was held in a number of academic institutes from Moscow and from Nizhny Novgorod. Как перелистать? Ага, спасибо. Motivation of my work is practically very close to that was announced in the previous speech. Many organic and non-organic substances, like greenhouse gases, air pollutants, biologically active materials, each exhibit a unique set of characteristic fingerprints or absorption bands in the mid-infrared. The remote sensing of trace amounts of all these substances require high brightness radiation source, at least luminophores, or better to have tunable lasers. As for solid-state lasers, the fiber configuration is the most practical for many cases, but still the spectral range of now existing fluoride glass fiber lasers is limited at less than 4 microns. A year before, I have reported at this very conference about our results in the development of a new type of a solid-state laser material, rare earth-doped chalcogenide glasses, for wavelengths exceeding 4 microns. Today, I'll speak about our latest results in bulk and fiber lasers of this type achieved during this year. Some words about the glass choice composition. The glasses we deal with are multi-component, germanium-based chalcogenide glasses. They prominent for their low phonon energy, resulting in wide transmission in the mid-infrared. This transmission consistently increases from sulfides to selenides and to telluride glasses. At this investigation stage, we have focused at selenide glasses and lasers at about 5 to 6 micron spectral range. The basic glass composition we deal with is shown here. This slide shows the rare earth ions we have managed to start lasing. All these 4 ions have one common feature: a mid-infrared transition starting from the first excited state and ending on the ground level. In selenide glasses, all these transitions are radiative, in contrast to traditional oxide glasses. And the lifetimes are 6 or even 7 orders of magnitude longer. They are measured in milliseconds. In this speech, I'll tell you about lasers based on cerium ions, terbium ions, and neodymium ions. Cerium ion has the simplest energy level scheme, but it requires resonant pumping at about 4 microns. We have used iron laser for pumping it at about 4 microns. Another option is high-power quantum cascade lasers, but still they are rather expensive. Terbium ion has a rich absorption spectrum in the near-infrared and can be pumped into any of these absorption bands. We usually use 2-micron thulium lasers for pumping, thulium fiber laser for pumping. As for neodymium laser, neodymium ion, for example, it also has a few absorption bands, but they are not suitable for pumping for a number of reasons. One reason that there are no efficient and available lasers at the needed wavelength. For this reason, we have to find a sensitizer for neodymium ions. This slide shows the emission spectra of these 4 ions. One can see that they overlap very much. All of them lie in between 4 and 6 microns. Cerium ion is distinguished for its highest emission cross-section in comparison to others. And neodymium ion is distinguished for its long wavelength shift, reaching 6 microns. We deal with bulk, we make our lasers based on bulk glasses and on fiber configuration. This slide shows the cross-section of such a fiber, of a cleaved end of such a fiber. The rare earth doped cladding is made of selenide glass and has a diameter of about 20 microns. The undoped cladding is made of sulfide glass. The refractive indices of all these materials are very high, and for this reason the Fresnel reflection from the cleaved fiber end is about 20%. It's, in most cases, it's quite enough for formation of laser cavity and for lasing. The difference between the refractive indexes of the core and the cladding is also big. For this reason, the numerical aperture of such a fiber is close to unity. The fiber is highly multimode. But despite the highly multimode structure of the fiber, the lasing in such a fiber is very close to single mode. We explain such behavior by the highly nonlinear properties of chalcogenide glasses. Optimized fiber and fiber configuration and pumping conditions has made it possible for us to enhance the output power of such a fiber laser to up to 150 milliwatts. Now I speak about terbium-doped fiber emitting at about 5.2 microns. Such a laser has an interesting feature. Despite continuous pumping, the lasing consists of a train of non-relaxing spikes. We explain such behavior by the upconversion between the two excited terbium ions in concentrated glass. Very similar phenomena took place in traditional silica fibers heavily doped with erbium or holmium. It's possible to suppress, if needed, it's possible to suppress such spiking by lowering terbium concentration and by introducing this or that negative feedback into the resonator. Now about cerium-doped fiber. Cerium has a very simple energy level scheme and no upconversion took place. For this reason, no pulsed operation is observed in this case. Here are the pump pulse and the lasing pulse. The pump source in this case was a low power continuous iron laser, and for this reason the output power is much less than in previous experiment, but it's one of the first experiments with cerium mid-infrared fiber laser. And this slide shows the spectrum of such a cerium laser. In case of high Q factor of the resonator, the laser emits at about 5 micron on the plot of the gain spectrum. In case of low Q factor, the lasing valence hops to the narrow peak of the emission spectrum at about 4.6 microns. Now I shall proceed to the most interesting from my point of view part of investigation. The sensitization of mid-infrared neodymium luminescence by terbium ions. The left figure shows the energy level schemes of both ions. There are two energy levels which are practically in resonance. We can pump terbium ions and there is energy transfer from terbium to neodymium. But the kinetic curves, the transit processes between terbium and neodymium at room temperature show that the energy transfer at room temperature is reversible. It goes from terbium to neodymium and back. For this reason, at room temperature, it was found impossible to get a high population of neodymium ions at the upper laser level to achieve laser action. But the situation has radically changed at liquid nitrogen temperature. In these conditions, the energy transfer becomes irreversible, becomes unidirectional, and lasing becomes possible. This slide shows the absorption of the co-doped glass sample at liquid nitrogen temperature. The absorption bands belongs to the sum of terbium and neodymium absorption, and the emission belongs to neodymium only. One can see that at the spectral interval between 5.5 and 6 microns, the absorption is already rather small, but the emission is big. This spectral interval is the interval where we hoped to get laser action. This is the sketch of the experimental setup. The bulk neodymium terbium co-doped glass of about 3 centimeters long was mounted in a homemade liquid nitrogen cooled cryostat with calcium fluoride windows. The laser resonator was formed by a concave metallic mirror, by a flat dielectric mirror, and a calcium fluoride prism which can be inserted into the cavity for tuning purposes. The pumping was held by a pulsed erbium yak laser emitting at about 3 microns, and the pumping has to be held by passing the non-transparent metallic mirror with some angle with the optical axis of the cavity. These two oscillograms show the pump pulse. Pump pulses, the black line, and the lasing pulses. The left figure shows the conditions close to threshold, and the right shows the pumping energy, corresponds to pumping energy several times higher above the threshold. Please pay attention to an interesting feature, that there is no lasing during the pulse, and the lasing begins a few hundred microseconds after the pump pulse ends. This time delay indicates clearly that the lasing ions are not terbium ions which are directly excited, but neodymium ions which are excited by non-radiational processes. And time is needed for energy transfer from terbium to neodymium. Of course, at high pump energy, both pulses overlap, but the lasing continues after the pump pulse ends. That's another proof that the lasing ion is neodymium and not terbium. This slide shows the input-output parameters of such a laser with two different outcouplers. The lasing wavelengths are indicated here. They are sufficiently longer than that typical for terbium. The highest output energy obtained was about 16 millijoules per pulse. This slide shows the tuning curve, ranging from 5.56 to more than 6 microns. This is the longest lasing wavelength for any glass laser for today. Now the conclusions. Practically significant output power up to 150 milliwatts was obtained from terbium-doped mid-infrared fiber laser emitting at about 5.2 microns. Spectral and temporal characteristics of a continuously pumped cerium-doped mid-infrared chalcogenide fiber laser were investigated. Spikeless laser action at 2 wavelengths was demonstrated. Terbium neodymium sensitization scheme was suggested and investigated. A new mid-infrared neodymium laser transition was started to lasing. Output energy up to 15 or 16 millijoules at 5.7 microns and wavelength tuning were obtained. These wavelengths complement well the lasing wavelength of terbium and cerium selenide glass lasers and are the longest for any glass laser reported for today. Thank you for your attention.
Thank you, Dr. Paul.
Okay, please go back to the oscillograms with before. Yeah, here. In this week pumping, you have the starting of kind of rotation oscillations, which is normal. But then you have a break of period here.
Yes.
So it seems that you have two competing lines of chemical matrices.
No. The lasing took place at wavelengths where terbium cannot lace. It's a longer wavelength. The time delay is required for non-radiative energy transfer from terbium to neodymium. And the lasing wavelength is different from that typical for terbium. So there is no competition. Only neodymium is lasing.
Please.
In the last approximately 2 decades, I have read a very large number of publications about the possibility of the laser generation in chalcogenide glass and fibers. But nobody has reported the real laser. What is your secret?
The secret is the secret is held by the chemists from Nizhny Novgorod. They have managed to make extremely pure glass.
semantic. Please, more questions?
Thank you for your talk. I catch you right that to work in team in one transverse mode for you is normal because you said about that your fiber is multi-mode regime.
Yes.
But you have in order the nonlinear properties of your glasses. You have the team 0, 0 regime of your generation, and it is normal situation. Yes. For this.
Yes, it's unusual. It was unusual for us, but it's an experimental fact that multi-mode fibers with high numerical aperture emit Gaussian beam with corresponding to 0 mode structure.
And there are no losses to
I suppose there are losses, but because the efficiency is sufficiently less from the theoretical limit, sufficiently lower than theoretical limit, but nevertheless, when the laser is well adjusted, it emits in this way.
Okay, could I answer one question about your spiky time domain diagram? You say about the upconversion process which give you such kind of the peaks.
Yes.
Could you explain more deeply the mechanism, the physical mechanism? Why it's so?
I suppose the mechanism is equivalent to that observed in, say, heavily erbium-doped fibers.
It is not modulational, but
It's kind of modulation. The experimental fact is that this spiking depends on the doping level. When the concentration is lower, the spikes became not so intensive and longer in time. But that's all what they can say for today.
Okay, thank you again. Now the third talk will be done now, Professor Buffetta.
Thank you for introduction. You see the title of my talk, and I will tell at first that we know that all fiber lasers are very useful instrument for many applications. Another achievement of last decade is the abrupt reduction in losses in hollow core fibers. This opens the way to make a combination of these two achievements, fiber lasers and hollow core fibers give us the gas fiber lasers. Up to now, it was already demonstrated a set of gas fiber lasers. One of them are based on inversion population mechanism, another on nonlinear effects like Raman gas lasers. But hollow core fibers enable us to use much more intensities of pulse radiation in comparison with pulse radiation in ordinary solid state core optical fibers. For this reason, it is strongly desirable to make the gas fiber lasers that will not include the fiber pump lasers based on solid core. For this, we can win about 3 orders of magnitude of optical power in such a case for fiber systems. And I will give a review of achievements in this field and of what can be done further. Here you see the you can compare the ordinary solid state core optical fiber, that is a side view, that is a cross section, and that is the hollow core revolver silica fiber, its cross section, that is mostly used now type of hollow core fiber. Using this graph, you can estimate the time necessary for optical loss reduction in glass. It takes about 3,000 of years. For optical fibers, several decades, and for hollow core optical fibers, approximately 1 decade. That is the cross section of the so-known of the quite modern structure of hollow core fiber with minimal losses. Here you see the spectra of the standard Corning SMF 28 fiber, red line. You can compare it with record low losses solid core fibers, silica fibers. That is values about 0.14 dB per kilometer, and DNANF hollow core fiber, that this abbreviation is nested, double nested anti-resonant nodeless fiber. I have shown cross-section of it here, this one. And losses in this fiber are below the standard value, but slightly higher than the record low loss level in solid core fibers. And using such fibers, it was already demonstrated the lasers based on inversion population in, for example, acetylene, that is a hollow core fiber. It is pumped by a laser, fiber laser, and that is output as a wavelength about 3 micrometers. It is pulsed model, and that is a continuous wave model of the same laser with the output about 1.1 micrometers, and the output power here was about 1 watts. That is cross-section of fiber that was used. In such a way, it was demonstrated generation in this number, in a number of gases at the wavelengths from about 1 micrometer up to about 5 micrometers. Dotted and dashed lines indicate the pump wavelengths, solid lines, the wavelengths of generation. Another type of hollow core fiber lasers, that is Raman fiber lasers. If we fill the core of the fiber with hydrogen, that is characterized by very high value of Raman shift, we can in one step overwhelm the distance between 1 micrometer up to approximately 2 micrometers. If we use pumping at the wavelength 1.5 micrometers, we can obtain at the output 4.5 micrometers. That is, this graph shows the typical for the hollow core fibers of this type. Computing dependence of optical losses against the frequency or wavelength, and solid lines are real optical losses in this fiber. This is a nice picture of the Raman fiber laser at the wavelength 1.9 micrometers. These colors are from the anti-Stokes lines, and that is the spectrum of this radiation. In more detail, we see here the output visible emission spectrum obtained after the dispersion prism, and that is spectra of the output radiation. That is a pumped wavelength, that is a Stokes wavelength, where the most part of output energy is concentrated. Efficiency of such lasers about 50% quantum, and that is an anti-Stokes spectrum. Hollow core fibers are capable to deliver a very high powers of propagating optical radiation, at least up to several gigawatts. This is 3 orders of magnitude higher than the maximum pulsed radiation powers generated by fiber lasers based on fibers with a solid core. Therefore, to fully realize the capabilities of fiber schemes, it is desirable to generate high power pulses directly in hollow core fibers without using other fiber lasers as pump sources. One of possible approaches to solving this problem is the development of gas discharge fiber lasers. The main problem here is the difficulty of maintaining plasma in a thin, about 100 micrometers in diameter core. What was already done in this field up to now? For maintaining gas discharge in hollow core fibers, experiments with radio frequency, direct current, and microwave electric fields were performed. Here you see a scheme of experiment with radio frequency electric field. Frequency 27 megahertz, wavelengths 100 meter approximately. You see the discharge in different gases. It was demonstrated that it is possible to start the discharge in such a way in optical fiber, in the hollow core optical fiber, but the generation lasing was not demonstrated. It was very difficult to start the discharge. You see, it was a special scheme to initiate the optical the discharge in such a fiber. And the length of the hollow core fiber with plasma column was only about 1 centimeter. Another approach to this to solve this problem is direct current excitation method. Direct current excitation carries the risk of contamination of gas with particles ablated from the electrodes over time, which is not a problem encountered in radio frequency and microwave-driven systems. But directly with only with direct current excitation, it was demonstrated the column of the plasma of the length about 1 meter, and even the optical amplification in a plasma. But the system was very complicated. You see here the scheme of the electrodes. That is the general scheme of the electrical scheme of the laser. That is 8 centimeter long optical discharge in a fiber. And here you see dependence of the output radiation against the length of the fiber. That is non-linear dependence, indicate the amplification, perhaps. But you need, in such a case, about 40 kilovolts source of pumping, which is not practical, of course. Another group from Limoges was demonstrated the approach of microwave radiation for excitation of discharge in hollow core fiber. But they rarely have demonstrated the discharge, that is the spectrum of it, but the length of discharge was no longer that 40 millimeter. What's the problem? The wavelength of microwave radiation is about 10 centimeter. The diameter of the hollow core fiber about 100 micrometers. You must to concentrate the energy of this radiation in a very small volume. It is, I can ask the optical, what is the minimal spots that the optical radiation can be focused to? About one wavelength. Wavelength 10 centimeter. We need 100 micrometers. For this reason, in this work, it was used the special excitation, special resonator for excitation that uses the surface wave that were propagating along the plasma column. But such a wave of excitation needs very high electron concentration. For this reason, is the restricted length of the plasma column, higher temperature of the plasma, and perhaps the lack of the laser radiation. Nevertheless, we consider microwave as a very appropriate way to excite the discharge in hollow core fibers, and we have suggested such a scheme for excitation of discharge. We have taken a waveguide, microwave waveguide, that is the direction of microwave propagation. That is a slot in the wall of the waveguide. The width of this slot may be made so small up to the diameter of the hollow core fiber. And in this, may be considered as a length for concentration of the microwave radiation. And we place here the hollow core fiber. That is the electric field here is perpendicular to the hollow core fiber. For this reason, we don't need high voltage to excite it. The voltage may be made so small as 100 volts, not higher. That is the picture shows the position of the hollow core fiber in purple between the edges of the slot. That is the electric field between that. We use in our experiments pure capillaries and hollow core fibers also. The diameter, the inner diameter of the hollow core fibers was up to 120 micrometers. And we succeeded to obtain the optical discharge. You see here the discharge in neon. That is the spectrum of the optical discharge in argon. it turned out that is the lines of argon, and that is the lines of nitrogen, that is impurity. And the length of the optical discharge was restricted only by the length of the slot in the wall side of the installation, of the microwave waveguide. We have measured the necessary electric fields to maintain the discharges in the hollow core fibers of small diameter, that is color lines. And we see that for different noble gases, these electric fields are quite applicable and may be estimated as 2.5 kilovolt per centimeter. I remember that the width of the slit may be 1 millimeter, that is order of magnitude lower, not 2 kilovolts, but 20 volts. And so if we compare all investigated methods of discharge initiation in the hollow core fibers, we can show such a table. Red is a good properties, black is a bad properties, and green unknown, that means. So we have for the first time proposed to use a special microwave waveguide system for excitation of electrical discharge. Using such a device, we have demonstrated the possibility of optical discharge initiation and implementation of stable microwave discharge in a hollow core fibers filled with noble glazes is a significant advance towards the solving of the problem of creating fiber gas lasers based on hollow core fibers. But I am pleased to inform you that we managed to demonstrate lasing in hollow core fibers just before the conference. Therefore, the next hour talk will be a kind of post-deadline paper, and I invite you to this talk. Thank you.
Thank you, Professor, for a very interesting presentation. And now we have time for questions.
Didn't you think about combining direct current and radio frequency current? For example, radio frequency can be used for pre-ionization of the gas inside the fiber, and the discharge can be
The main pump.
Lower voltage than
I have understood. Thank you very much for the question. Unfortunately, I missed to tell you that we have used the mercury lamp for pre-ionization of the noble gases. It is, I believe, much simpler and more reliable.
Is it possible to maintain this type of discharge at high pressures, say near atmosphere?
Sorry.
Can you maintain this type of discharge in hollow core fibers at the pressures near atmosphere?
We have,
The next question.
I have understand.
Can you estimate what is the reduced electric field? What is the value of reduced electric field in your discharge in the hollow core fiber?
I hope I have understood your question. We have measured the dependence. That is not Paschen curves. It is the dependence of the electric field necessary to maintain, not breakdown, to make breakdown, to break, but to maintain the the discharge. And you see that the minimal value of the electric field is near approximately 50 torr. Here it is much higher than for example, microwaves. And in the case of helium, it is about one half of, more than one half of atmosphere. So it is quite possible. The problem is when you place the fiber in the slot, the air around the fiber can also be give a breakdown, and
Okay, maybe one more question. Okay, thank you again. So the first session is closed, and we have time for coffee break, simply not more than 15 minutes. After that, we can be here for continuing our
Вы на следующий, да?
You are currently the only person in this conference.
Okay, dear colleagues, I think we should start. We have given handsome 3 minutes for latecomers. So I am Gregory Sokolovsky from Yoff Institute, and my pleasure to preside the second section of today. And the first talk is, Professor Buffer put it, as a post-deadline talk, which is shorter than his previous one, and he will tell us about his new results. So, Professor, you have 15 minutes, I believe.
Thank you. Thank you for introduction. This work was fulfilled in Prokhorov General Physics Institute, Indiana Fiber Optics Research Center, and in gas discharge laser laboratory of the Prokhorov General Physics Institute together. My talk will include the message about the first demonstration of the gas discharge fiber laser. I will tell about some words about the revolver type hollow core fiber, fiber itself, then about the microwave driven discharge in this fiber, about the laser cavity for this laser, and show the spectrum and time dependencies of the xenon gas discharge fiber laser radiation, and conclude my talk. I have already shown such a picture. That is a system of electrical pumping of the gas discharge in hollow core fiber. That is a hollow core fiber with 9 capillaries that form the cladding, the reflective cladding of this fiber. The diameter of the core is 130 micrometers. That is the microwave waveguide. That is direction of waveguide of microwave propagation through it. That is a slot in a side wall of this waveguide. That is a hollow core fiber placed into the slot. And this is the mercury lamp for ignite the discharge, because the electric field to start the discharge, to break the gas, is always much higher than the electric field necessary to maintain the discharge. That is the experimental setup microwave part. That is the magnetron. That is a microwave waveguide with some apparatus. That is, here is the slot with a cover now. The total length about 1.5 meters. Of course, it is not the system for practical use, but this system is for laboratory experiments. That's the optical discharge in a waveguide. That is the side wall of the microwave waveguide. The color of glow shows that this discharge in nitrogen. That is the scheme of the gas discharge fiber laser. That is the slot in the microwave discharge. That is a hollow core fiber. The ends of the hollow core fiber, the length about 1.5 meters, are placed into the tiny vacuum chambers to evacuate the hollow core fiber and to fill it with proper noble gases that is necessary for generation. That is mercury lamp for ignite the discharge. 4, it is a high reflective mirror that is simply polished aluminum, metal. The output mirror is multi-layer mirror, that is the transmission spectrum of it. You see that it transmits the wavelengths about 2 micrometers, about 1.7 micrometers, about 1.5 micrometers, and around 3.5 micrometers. The ordinary wavelengths of generation of xenon laser, gas lasers. That is the visible spectrum of the discharge in the hollow core fiber filled with the helium, with a mixture of helium, argon, and xenon, 100 to 10 to 1 mixture. The total pressure 130 torr. The low part show the calculated spectrum of this mixture without taking into account the small dimension of inner diameter of the hollow core. You see, we can comparing, we can evaluate what lines of luminescence we see in really in experiment. That is the impurities of the mixture. So, in such a scheme of the optical scheme, we obtained the laser generation. What we have obtained directly. That is the oscillogram of the microwave pump radiation. Pump radiation was pulsed 400 hertz. The duration of the pulse was 20 microseconds. It's not right, but 20 microseconds. That is microwave pulse. Blue line, that is the signal from the optical resistance in the absence of generation, and red is the signal when resonant mirrors are aligned. Blue line, high reflection mirror tilted. You see. But what was the wavelength of generation? That is a measurement using the spectrum analyzer in the range between 1 micrometer and 2.4 micrometers. You see the line of generation, and in the narrow band region, that is 26.8 nanometers. Line width was around 0.2 nanometers of the order of the wavelength resolution of the spectrum analyzer. The mean output power, average output power, was around 1 milliwatts only, but we hope that the future experiments enable us to make it better. So, for the first time, a new type of laser has been developed, a gas discharge fiber laser. The results obtained open up the possibility of improving the design of such lasers in order to create more compact and efficient models. In the course of further research, it is possible, by varying the gas composition of pump intensity, as well as using spectrally selective resonators, to obtain xenon laser generation at other wavelengths, primarily in the range of 3.3 up to 3.5 micrometers. And finally, the possibility of using of other gases, for example, neon, to create gas discharge fiber lasers remains to be explored. We believe that gas discharge fiber lasers, using combination of the advantages of the fiber and gas discharge lasers, will find numerous applications in various fields of science and technology. And if we return to the table from the previous lecture, we see here two red marks. We obtain, no doubt, laser generation and optical amplification in such a scheme. Thank you.
Thank you so much. So, thank you for being very much in time. Much appreciated. We have time for questions, please. Probably I'll break the ice. You tell that you foresee options to make the system more compact. Can you please tell about that?
You see, of course, it is not necessary to use the slot system for pumping. It is quite possible to use the capacitor system. We can substitute the edges of the slot by plain electrodes, and it will be quite compact. For example, in Tashkent, approximately 30 years ago, it was demonstrated such a scheme for another kind of gas lasers. And so it is nothing new in this. It is possible.
Very good. Any more questions? Well, it seems that you made it too clear.
Mm-hmm.
Thank you so much. The next talk comes from Novosibirsk, and the program terms it should be Sergey Babin, but I think it is Professor Dostovalov instead of him.
Not professor.
Okay, Professor to be. Okay, so the title of the talk will be on the screen in a minute. I believe.
Thank you for introduction. And first of all, I would like to thank the organized committee for invitation. Unfortunately, Dr. Sergei Babin was not able to give this talk and asked me to present our results of fiber break ratings inscription by femtosecond laser radiation for sensors and laser applications. This outline of my talk after short introduction for basic mechanism of femtosecond modification of transparent materials and FBG inscription using this technique. I will present the results of sensors development based on FBG inscription in multi-core fibers, and also laser developments based on inscription in 2 and 7-core fibers for Raman fiber laser development, and a turbine doped fiber laser development based on inscription in active fiber. But before discussing these results, I would like to remind basic principles of femtosecond modification of transparent materials. Nowadays, with development of femtosecond lasers, we can obtain high power radiation for ultra short pulses. It means that we can obtain several hundreds of femtosecond pulse duration and microjoule pulse energy, and for this reason we can obtain intensity of 10 terawatts per centimeter squared. At such intensity, initially transparent glass starts to absorb laser radiation, and it leads to fast heating and subsequent melting and resolidification of materials. And depending on the pulse fluence, we can obtain 3 main modification in glass. The first one is the tropic refractive index change. Here you can see, sorry, doesn't work. Pointer doesn't work. How? Okay, yes. Here, after increase the pulse energy, we can obtain barefidgin formation in this area and void formation and at higher energy. Here you can see the time scale of different physical processes that take place during femtosecond modification of the materials. And it should be noted that absorption of the photons occurs before the carrier photon scattering. It means that energy dissipation from focal area is minimized in this case, and for this reason the energy absorption is most efficient, and this provides the high precision of these methods. And moreover, we can use high tightly focusing by microscope objective that presented here, and also because of multi-photon nonlinear process of absorption, we can localize our modification area inside the volume of glass. And for these facts, we can obtain parameters, area of experimental parameters presented here, where we can change the refractive index without material damage. And for this reason, we can obtain possibility of 3D structure formation inside materials, and also obtain the high reproducibility of inscription, because this regime does not depend on some defects in the materials and so on. For this reason, we can use this technique for inscription fiber break ratings. Shortly remind, fiber break ratings is a periodic structure inside fiber core that reflects wavelengths at certain wavelengths. Depending on this expression, that depends on period of wavelengths and refractive index, effective refractive index. For this reason, such type of gratings can be used as laser mirrors and also as sensing element in sensors, fiber sensors. Because we can use this FBG as sensors because of compact size, immunity to electromagnetic interference, and capability to perform many distributive sensing. And traditionally, FBG was inscribed by ultraviolet radiation, and using phase mask technique that presented here, we use phase mask to produce interference pattern in the core of the fiber. And in this case, the period of FBG depends on the period of phase mask that is not convenient for inscription different FBG with different wavelengths. And alternative method is point-by-point inscription that presented here. In this case, we can produce periodic structure by using single pass, single laser pulse, and pulling the fiber with constant speed. And in this case, the period of ABG depends on the velocity of translation and frequency of laser pulses. And in this case, we can change the period of ABG very easy. We can change velocity and obtain different ABG in this case. And additionally, using femtosecond radiation, point-by-point writing technique provides additional advantages, such as desirable grating length, period, profile, also writing through transparent coating that is transparent for infrared radiation, and also possibility of 3D structure formation inside materials. Here you can see our experimental setup. Femtosecond radiation from femtosecond laser was focused by high numerical aperture through a transparent ferrule with polysheet from one side to for effective focusing inside the fiber core. Here you can see the image obtained by microscope of our structure, and using this technique we can produce different type of ABG with different lengths, from short, very short, 100 microns, to very, not very long, but quite long, 50 millimeters. And as I said before, our theme of our topic is inscription in multi-core fibers. And multi-core fibers is very important for sensing applications because of it allows us to measurements of different parameters, pressure, temperature, and allow us to space division multiplexing in different points. And also sensors in multi-core fibers provides opportunities to structural health monitoring of different constructions, for example, in composite materials or in non-invasive surgery, for example, to tracking the shape of the different medical devices during the operation. The principle of operation of such sensor is quite simple. If we have different FBG inside cores, after binding the fiber, one FBG period of one FBG will be increased due to stretching, and other FBG will be compressed, and we can measure wavelength shifts, as I mentioned before during the formula that I presented before. And we can after measurement this value, we can calculate not only strain in this point, but also direction of this strain. And using Fresnel's array equation, we can calculate distributed strain along the fiber, and such manner we can reconstruct the whole fiber shape in that case. Here you can see the short video that we, okay, it works, yes. It's laser spot. This is side course, and here you can see the structure that was inscribed in the fiber core. And for this short demonstration, we used spun helical core fibers. It means that this fiber has straight central core, and side cores has a helical rotation along the fiber. And in this case, we can focus our radiation only in one core, a side core, and pulling the fiber. And using this technique, we can inscribe different FBG in different cores. For example, if we see here, from that spectrum, it is a spectrum of FBG array inscribed in different cores. It means that we can inscribe without stopping the laser, yes. But if we skip some cores after rotating side cores, and allow us to inscribe the FBG array only in individual core. And here you can see different FBG inscribed only in one side cores. And here you can see the cross-section of the fiber with modification that was presented here. As I mentioned before, we can use such type of gratings for 3D shape sensors. And here you can see the results of reconstruction of different 3D shapes, spiral shapes with different diameters and step along the fiber. And in all cases, we obtained around less than 2% of error. And also, as I mentioned before, it's very important. One application of such sensors is medical devices, and we try to adopt our sensors for that, and we put these sensors in a flexible part of medical devices of papillotome, is flexible part of that. Here you can see the fiber inside. And we reconstructed this form in different shapes and also obtained quite good results, less than several percent. But of course, inscription of OBJ not only important for sensors applications, but also for laser applications. For example, for coherent beam combining, that is hot topic of laser development now. Here you can see quite recent paper, nice paper of coherent combining. But in this case, very complex and very bulky scheme for coherent combining is used to ensure the right phases for different beams. And in our opinion, inscription of OBJ in active fiber in different cores and using coupled cores active fiber is an attractive solution for that task. And moreover, as was presented, that was shown in our group previously, that using multi-core fibers with coupled core, we can increase the influence of different nonlinear effects on broadening of the laser line width. Because kernel nonlinear coefficient is inversely proportional to mode field area, as you can see here. And for this reason, if we increase the number of cores in multi-core fibers, we can increase the mode field area. And for this reason, we decrease kernel nonlinear coefficient. And it was shown in our group that line width of Raman twin core fiber is several times smaller than laser based on single mode fiber. But in last case, for cavity, authors use fiber loop mirrors that is not selective elements, and we propose to use fiber gratings that is wavelength selective elements. And for this scheme, we propose to use quite not complex, but some specific wavelengths array, OBJ array that consists of two OBJ. The first one was inscribed in one core, and another one was inscribed with a small shift of around 5 millimeters in that case. And cavity was formed by half kilometers twinkle fibers with inscribed array here and an angle cleaved fiber from that side. And as we see from that picture, that output spectrum of laser radiation consists of many narrow peaks with width less than 20 picometers. It means also resolution at low power. With increasing the power, the line width of the laser increases too, but in case of using high reflective OBJ in one area, we can obtain quite less line width in comparison with fiber loop mirror. It means that we can tailor spectral characteristics of our laser by inscription of OBJ in different cores or only increase in one core. And the next step was the Raman fiber laser based on 7 core fibers was investigated. In this case, the fiber cavity was formed by 1 kilometer long 7 core fiber with FBG array that was inscribed from one side and from another side. As in previous case, the FBG was located with small shifts in this case, and as I mentioned before, it can help us to tailor the spectrum characteristics in this case. Here you can see the output power that reach 2.5 watts at 70 watts of pump power, and here you can see the output beam pump radiation from all cores, because we don't have FBG for pump, and only radiation from central core in case of Stokes radiation, because in central core was not FBG for Stokes radiation. And you can see here, as in previous case, in case of low power, we obtain multiple peaks generation with very narrow lane width. And also, as I mentioned before, the lane width of our laser is smaller than in case of single mode fiber that was presented here. And finally, I would like to present the results of ytterbium fiber laser based on FBG inscribed in 7 core fibers, active fibers. And in this experimental setup, we use cavity was formed by 7 core ytterbium doped fiber with different lengths, and the FBG was inscribed in different fibers. We use different fibers. The first one is uncoupled cores. Here you can see it means that distance between the cores is large, and the coupling between different cores is minimized. And another one is multi-core fibers with coupling. It means that radiation from one core can transmit to another from a certain distance. And using different lengths of the fiber, we can obtain the same output power for both of fibers, but output spectra are different. In case of without coupling, here you can see here, the output spectra consist of many line widths that was connected to the spectra of FBG. I should mention that FBG that was inscribed in multi-core fibers have different wavelengths because of some shifts in errors in inscription. It means that it's quite complex to write the same FBG with the same spectrum. Yes. And for this reason, we have some shifts between different FBGs, and in case of no coupling, different lines corresponds to different FBGs spectrum. But in case of strong coupling, we have the same FBG spectra with small shifts between them, but generation light has only a single narrow lane width. Yes, I agree. Single narrow lane width. That corresponds to geometric mean of FBG spectra that was presented by dark light here. In conclusion, we developed versatile method of femtosecond based inscription of fiber break ratings in passive and active fiber, and based on this technique, we developed different sensors, 3D shape sensors for structural health monitoring. And also we propose different scheme of Raman fiber laser based on these multi-core fibers, and also new effects of spectral collapse of 7-core ytterbium fiber was demonstrated. Thank you for your attention.
so much. The talk is open for questions. I'll give you a microphone for the sake of online.
Thank you very much for your presentation. You modify the the properties of dielectrics, but what happens with the optical lenses which you use to focus the light?
Sorry,
Which kind of optics are you using to modify this high power light on new materials?
We use typical optics with typical optics because such big intensities can reach only in focal area only, because you need to focus your radiation also to reach such intensities. And for this reason, typical optics work in our case at such, yeah.
What is the physical mechanism of refractive index change under laser action? Is the refractive index decreased or increased? And what happens in the fiber cladding? Are fiber gratings formed in the cladding too, or only in the core?
Yes. As I mentioned before, we need to reach intensities to start the multiphoton ionization and absorption process. It means that we work only in focal area of our in the bulk of the material. Yes, here you can see the modification inside the bulk. It means that on the surface of the cladding of the surface of the fiber, the intensity is very low because our beam focused by high numerical aperture. And it means that cladding does not modifies a lot, let's say. Only in the core we can see quite strong, quite distinctive modification. About mechanism, there are different mechanisms of refractive index change. The first one is compactization. It means that glass naturally consists of different ring structure, seven member rings, 6 member rings. After modification, this number of rings decreases to 4 or 3. It means that density of glass increases in modification, and if density increases, it leads to increase the refractive index. But it depends on the materials. For example, for fused silica, you can obtain increase the refractive index in focal area, but in crystal it doesn't work. In crystals, you cannot achieve a high refractive index in focal area because it's crystal. It's minimal. How to say?
Already compact.
Yeah. It means that in crystal we can only decrease refractive index. And for this reason, in crystals, to write waveguides, we need to write claddings in case of core. Yeah.
Okay. I have a question as well about the Q factor of your ratings, because when you have a phase mask, then the Q factor is well known. But when you just pull it, so you depend on stability of this pulling. Can you comment on that?
Yeah. Yes, it's the right questions, because You need to use very precision linear air-bearing precision linear stage. It means that you cannot use common stages like standard. It doesn't work. You should use only aerotech with high precision, with high encoder, let's say, with top characteristics. Only in that case it will be work. Yeah.
Okay. So thank you so much. We have no time for more questions, and we go to the next talk, which will be delivered by Dr. Gladyshev from Prokhorov Institute. So, Doctor, we have 20 minutes. Please keep time.
Thank you for introduction. My talk will be devoted to mid-infrared supercontinuum generation in hollow core, in gas-filled hollow core silica fibers. So now it's well known why do we need mid-infrared laser sources. Many molecules have absorption features in the mid-infrared range, and it's not surprising that mid-infrared laser sources are finding many applications in spectroscopy, biomedicine, remote gas analysis, environmental monitoring, and so on. So there is strong demand for laser sources at wavelengths more than 2.5 micron approximately. And of course, we would like to have fiber lasers because of their well-known advantages such as good beam quality, compact design, long interaction length. When we talk about fibers, we usually mean silica fibers, but it's also well known that silica fibers are not applicable at wavelengths above 2.5 micron. This supercontinuum spectrum of a commercial source based on silica fibers shows very well the working range of silica fibers, but we need to go to longer wavelengths. So silica is an obstacle for us now, but we need to avoid using silica, and here we have an elegant solution. We could remove only silica-based core of the fiber and keep the cladding of the fiber made of silica glass. In this case, we have such advantages as we don't work with soft glasses, and we still are working with well-developed silica glass technology. At the same time, we avoid all fundamental limitations imposed by silica glass in the core. We extend spectral range of applications of such fibers, but to have simply a hollow core in the bulk glass, it's not enough to have low enough losses. And to have low losses in such fibers, proper cladding design should be done. There are many designs of hollow core fibers that were proposed in literature. This topic started from photonic bandgap fibers, when cladding of the fiber has like a photonic crystal, which prohibits propagation of light in the cladding, and light is localized in the hollow core. But this kind of fibers suffer from a relatively large portion of the light is penetrating to the cladding and interacts with silica. In an attempt to reduce amount of silica in the cladding, this kind of fibers were developed, so-called Kagame fibers. Such fibers are not photonic bandgap. Their cladding don't have photonic bandgap, but nevertheless, such fibers localize light in the hollow core, and especially when they found that negative curvature of the hollow core boundary should be implemented. In 2011, in Fiber Optics Research Center, our colleagues proposed this kind of design, which we call revolver fiber, and this design performs even better than these designs, but have a simpler structure, and it's easier to fabricate, and it has more reliable properties. So with such a complex structure, you have many possibilities to have something wrong, and properties of such fiber will be not as you expected. In this type of fibers, you can design the fiber, and with high probability you will have what you expected. And this simple design became a starting point for developing a new set of fibers based on this design. Now we work with this kind of fibers, revolver fibers, with single ring of non-touching capillaries. This kind of fibers is promising, especially for mid-infrared spectral range. It provides quite strong localization of light in the hollow core with a minimal interaction with silica capillaries. It's still simple design and have well predictable properties. So, how to generate mid-infrared light in gas-filled hollow core fibers? One of the approaches is to use intense few-cycle pump laser pulses at well-developed, well-known laser wavelengths, for example at 1 micron, ytterbium laser. And in such high-intense pulses, propagating in gas-filled hollow core, the gas can be ionized, and this plasma modifies the dispersion in the fiber, and phase-matched dispersion waves could be generated in the mid-infrared. For example, in this publication, the authors managed to pump the neon-filled hollow core fiber with 1 micron radiation and generate radiation around from 3 to 4 micron. But efficiency of the process was very low. You can see that its efficiency about 4 to 5 orders of magnitude lower than in the pump. Another approach is to use mid-infrared pump laser pulses, femtosecond pulses. In this case, in this work, researchers used approximately 2.5 micron radiation, 100 femtosecond pulses in argon-filled hollow core fiber, and in usual way by mechanism of solitol self-compression, they make a supercontinuum generation around these wavelengths. But in this case, yes, efficiency of the process and efficiency in the mid-infrared range is improved, but you should already have mid-infrared laser source, intense mid-infrared laser source. And this is usually an optical parametric oscillator, which adds significantly to the complexity of the system. And to simplify the setup, we need to we want to generate mid-infrared femtosecond pulses in the hollow core fiber itself, not using OPA. And for this, we could use Raman conversion in light molecular gases, which have very high Stokes shift, and using such gases filled to the hollow core, one can generate mid-infrared light just in a few cascade of Raman scattering from well-known wavelengths. For example, in the literature is already there are many works demonstrating this conversion from sources at 1 micron on 1.5 micron by Raman scattering or single cascade or two cascade Raman scattering. Many wavelengths in the range from 2.8 up to 4.4 micron have been generated. And this is one of the examples from erbium fiber laser at 1.5 micron. We have generated 4.4 micron in hydrogen filled hollow core fiber, and with good quantum efficiency, 53%, quite high output power, average output power 1.4 watt at 4.4 micron from such a fiber. But all this demonstration was in nanosecond regime. And nanosecond pulses is not good enough for producing supercontinuum generation. We need shorter pulses, femto or picosecond pulses. How to achieve this? Raman conversion of femtosecond pulses have some problem. In femtosecond regime, Raman conversion becomes highly transient regime, which demand to increase the intensity of the pump. On the other hand, because of high intensity radiation, this high intensity pump promotes competing nonlinear effects based on kernel linearity, which could prohibit Raman conversion. But there is a known solution for this problem. Femtosecond pump pulses at, let's say, 1 micron can be chirped, linearly chirped. Then these longer pulses and less pulses with less intensity could be converted to Stokes wavelengths. Then residual pump light can be filtered out, and chirped Stokes pulses can be used directly on or compressed to femtosecond pulses in the mid-infrared if needed. And this this solution is is working, and it's shown in many works. In hollow core fibers, this method also have been applied quite recently. For example, in this work, researchers used femtosecond pulses at 1 micron and generated 40 microsecond pulses at 1.8 micron in hydrogen filled hollow core fibers with very good quantum efficiency. Also, we extended the wavelengths into the mid-infrared further by using deuterium filled hollow core fiber, pumped also at 1 micron by chirped femtosecond pulses, and we have generated approximately 2.7 micron radiation sub-picosecond pulses with 10 microjoule pulse energy in the mid-infrared. Next step is to broaden the spectrum of this laser. So here we have the output spectrum. Pump radiation at 1 micron is filtered out, but we have here first Stokes at 1.48 and the second Stokes at 2.7 micron. So now we want to broaden the spectrum of these lines. Our usual setup consists in, is very simple. So we have pump laser, which is ytterbium femtosecond laser at 1 micron, which is the radiation of this laser is focused to the hollow core fiber that has small gas cells at the end. These cells provide us opportunity to fill the gas inside the hollow core, and cells have windows to couple and decouple the radiation. So, and output radiation is investigated. Well, we measure spectrum, power, different components, and so on. Here is the loss spectrum spectrum of optical losses of hollow core fibers. It consists of some transparency bands separated by high loss peaks. And the idea is to have pump wavelengths in one transparency band, the first Stokes lines in the second, in the next transparency band, and after approximately 2.5 micron, we have a very wide mid-infrared transparency window, and we would like to have second Stokes lines there and broaden them. Here is an example of Raman conversion in deuterium filled hollow core fiber when the pump radiation was, pump pulses were chirped to duration 12 picoseconds. In this case, we see pure Raman scattering. So this is the pump radiation at 1 micron, first Stokes 1.5 micron, and 2.7 second Stokes. When we reduce duration of the pump pulses, we can see that Stokes lines and pump becomes broader, and the lower the pump pulse duration, the wider the broadening. But if we apply too short pump pulses, Raman scattering, at least in the second stage, becomes suppressed. So generally we have such typical regimes. At pump pulse duration around 6 to 12 picoseconds, we have pure Raman scattering. At pulse duration around 1 picosecond, we have multi-band supercontinuum generation. But if pump pulses go below 750 femtosecond, the second mid-infrared radiation is suppressed in Raman scattering. And in this case, in deuterium filled hollow core fiber, we reached supercontinuum generation with spectral coverage up to 3.3 micron. 14% of pump quanta were converted to wavelengths above 2.9 to this part of the spectrum. But we would like to extend this wavelengths even further. To do this, we decided to use a mixture of gases. So deuterium was mixed with hydrogen in the hollow core with this ratio of partial pressures. Again, when we use long pump pulses, 12 picosecond, we have some new lines. So black spectrum is usual spectrum for deuterium filled hollow core fiber, and red spectrum for mixture. And here we have a new spectral component, 3.9 micron, which is due to cascade Raman scattering. One cascade is on vibrations of deuterium molecule, and next cascade on vibration of hydrogen molecule. In this case, we also have quite high pulse energy in the mid-infrared, very good quantum efficiency and picosecond pulse duration here. So if we this spectrum is reproduced here in the mixture and with long pump pulses. And again, if we start reducing the pump pulse duration, we have spectral broadening, and for pulses, pump pulses with duration of around 1 picosecond, we have quite very broad spectrum. So it will be compared here better. So this gray area is a spectrum obtained in deuterium filled hollow core fiber, and red spectrum is in the mixture, deuterium and hydrogen. We improved spectral power density in the mid-infrared, and long wavelengths of the supercontinuum was extended up to approximately 4 micron. And there was another finding in the mixture of deuterium and hydrogen. Here we see the spectrum, output spectrum of the Raman laser filled by deuterium and hydrogen mixed in this ratio. And we can see standard components for deuterium, first stocks in hydrogen, second stocks Raman in deuterium, and our wanted wavelengths at 3.9. But also we have some spectral component here, and this component was always present in our experiments at some small level, but only recently we realized that it's due to hydrogen deuterium molecule. And this component also is Raman shift from the pump, one cascade in deuterium and another cascade in vibrations of HD molecule. If we increase the pump power, we have this intensity of these lines much increased. And this peak also is a double cascade in HD molecule. So the question is how this molecule appeared in our system. And for now this is unresolved question, but we hope that our Raman laser initiates, stimulate atom mixture. So change atoms between these two molecules, deuterium and hydrogen. So, conclusions, mid-infrared supercontinuum source is demonstrated in hollow core fibers filled by mixture of deuterium and hydrogen. The source pumped by easily available femtosecond laser to 1 micron. Efficient conversion to the mid-infrared is promoted by Raman scattering, and spectral broadening was achieved due to kernel nonlinearity. Spectral coverage up to 4 micron is achieved. Formation of HD molecules in the mixture in the hollow core fiber was observed. Thank you for your attention.
Thank you. We have time for just one short question. Can you comment, please, on long-term stability? Because these molecules are quite small, so they can escape your fiber. So you need pumping.
From the fiber, yes. During the stability is enough to work during the day, but the next day we need to
if it is a
pressurize
product,
the fiber slightly more.
Okay, thank you. Thank you again.
One simple question.
Make it quick, please.
Yes, about the physical mechanism of the generation of supercontinuum in the hollow core guide. You mean that you generate supercontinuum in air?
No. Inside the fiber. No. In the hollow core, we evacuate the air and fill hydrogen molecular gases, hydrogen, deuterium, and supercontinuum is generated in these gases.
Yes.
Okay, thank you. So, next talk comes again from Prokhorov Institute, Professor Melkoumov. You have 20 minutes.
Okay, thank you, Mr. Chairman, for introduction. My talk is devoted to advances in bismuth-doped fiber lasers and amplifiers, and part of this work had been done in Fiber Optics Research Center, and some other results were obtained in other different groups from United Kingdom, France, and Canada. So this is outline of my talk. First of all, I would like to give you a brief introduction concerning motivation of this work, why we should try to investigate new materials like bismuth. Then I would like to present results concerning simple bismuth-doped fiber amplifiers and lasers. And after that, I will talk about possibility to increase the bandwidth of these amplifiers, namely how to get it wider, how to obtain wideband bismuth doped amplifiers, what is possible strategies for that, and what is results. After that, I would like to present a couple of possible commercialization of bismuth doped fiber amplifiers. And finally, I would like to say a few words about new type of pumping of this type of fibers, namely it's cladding pumping, because for many years all bismuth doped fiber lasers and amplifiers were pumped into the core, and it make the structure quite complex. And recently we developed a new type of fibers which can be pumped into the cladding. So the main motivation is driven by the increased capacity of optical networks. And here you can see the growth of internet traffic in the world. And you see that the growth approximately 10 times per decade. So it means that industry should support such a great demand for data traffic growth, and it means that they should find a way how to improve their networks to increase their capacity. If we look at the optical transmission window of silica-based fibers, which are typically used in telecom systems, you will see that there is an optical window here from 1.27 approximately up to 1.7. And you see that not all this window is occupied by efficient optical amplifier. And now in the current system, in current telecom system, they use typically only erbium for amplification of optical signal. And it means that only 20% of available bandwidth of silica-based fiber can be effectively used for data transmission. Of course, for short-range system, you can use, for example, larger region, but if you want to obtain a long-distance data transmission system, you need to have an optical amplifier, and only certain region from this broad range can be used. So it means that industry needs some kind of good, effective optical amplifiers for all this range. Starting, for example, from maybe 2005, several groups developed a lot of kind of bismuth-doped glasses and fibers. And after 10 years of this work, it was shown that only 4 types of glasses all these glasses are based on silica, and only 4 types can effectively demonstrate not only luminescence but optical amplification and gain. And this is bismuth-doped glasses. This is silica-based glasses doped with bismuth and doped with aluminum, phosphorus, pure silica-based glasses with bismuth, and highly doped with germanium. And here you can see the luminescence spectrum of all these 4 types of compositions. Of course, to obtain this luminescence, we need to apply different pump wavelengths. Now I would like to present results on simple bismuth-doped fiber amplifiers, which were based on this type of glasses. Here is the simple scheme of single-stage bismuth-doped fiber amplifier. In fact, any kind of fiber amplifier based on active element can be represented like this. So the scheme is quite simple. This is the active fiber, 2 elements to launch pump radiation and signal for signal input and output, isolators to prevent parasitic radiation and lasing. And for example, for bismuth doped fiber, we can use different possible pump wavelengths, which is shown here, depending on the composition of bismuth doped fibers. So the pumping scheme can be forward, backward, or bidirectional. Typical fiber lengths for bismuth doped fiber lasers and amplifiers, starting from 50 meters up to 250 approximately. But I would like to stress that this scheme is only core pumping. So all the radiation from signal and for pump is in the core. So this figure shows just very beginning results for amplification in aluminum doped bismuth doped fibers. This is the authors from Fiber Optic Research Center measured only on-off gain here, which is here and here for two different kind of samples. And you can see that the gain peak is near approximately 1.15 microns. For pumping of this device, they use radiation from ytterbium doped fiber laser near 0.6 micron approximately. So unfortunately, on-off gain is not the real gain. So in fact, if we look at the real gain, if we look at the net gain of this device, we will see that the net gain is much lower than on-off one. And also you see that the negative gain means that the absorption became higher when pump is on than initially. So after that, if we consider to another composition of glass, this is phosphorus doped glass with bismuth, this one, and for germanium doped glass, silica-based glass, of course, with a lower concentration of germanium, we can see that here we obtain quite good gain, about 25 dB per amplifier, and quite good spectrum of amplification, about 40 nanometers bandwidth. And the noise figure which describes the optical noise of the amplifier, and the lower the noise figure, the better, is also not so bad. So this is about 6 dB, and here we see that the noise figure is lower than 6 dB. So if we compare the same in erbium doped fiber amplifier, we will see that the gain of the amplification is more or less similar, and for C-band amplifier in erbium, we obtain a little bit lower noise figure, but for L-band amplifier, the noise figure is more or less similar. So it means that this kind of amplifier can compete with erbium doped fiber amplifiers in real telecom systems. And finally, for simple bismuth doped fiber amplifiers, we developed a highly germanium doped silica-based glasses. And for this kind of glasses, the results is presented here, and you can see the amplification band here is shifted to the longer wavelength with the maximum around 1.7. The noise figure is a little bit higher because of quite high splicing losses between highly germanium doped fibers and standard telecom fibers. So it means that the main reason for this discrepancy is due to splice losses. The level of peak gain is similar, and also you can see here the dependence of the gain on and the power conversion efficiency on into signal power. So what we have up to 2015, and you can see that we can cover several regions in the fiber transparency window. Here you see also for comparison the amplification in erbium doped fiber amplifiers. And now we can cover 3 additional regions. So I would like to stress that all this fiber and all these glasses which demonstrate amplification and lasing were produced only by MCVD technology. But in fact, you also can see that there is a gap, and also we need a lot of number of amplifiers to cover all this transparency window, which is not convenient for industry. In fact, they would like to have only one amplifier for all bandwidths. So we need to improve the bandwidth at first, and then improve the noise figure, and what we can do with that. So now I would like to turn to wideband bismuth doped fiber amplifiers, what we can apply to obtain more widths of the amplification, and what is the results. So here you see possible strategies to increase the amplification. First of all, we of course can find some new glasses, but it's still under construction, and of course a lot of people try to think about it and to do, but right now only 4 composition is available for effective amplification with bismuth. So another possible strategy is inhomogeneous broadening of bismuth active centers, and I will show you some results in this direction. Additional possible way is to use multiple active centers. For example, we can combine amplification from several different bismuth active centers, because now we know about 4 kinds of bismuth active centers associated with aluminum, phosphorus, silica, and germanium. And finally, we can combine the amplification of bismuth, for example, with other element, namely, for example, erbium. Also, we can put all these active centers in one fiber, or maybe in separate fibers. Additionally, we should optimize the pump wavelengths, and if we need very broadband amplification, probably we can use multiple pumping wavelengths. So in this case, we probably can achieve widest possible gain in one amplifier. Now I would like to show you results towards the investigation all these strategies, very briefly, of course. So first of all, this is a variation of gain spectra in bismuth active fibers doped with phosphorus versus the possible variation of pump wavelength. And you can see that varying the pump wavelengths, we obtain variation of gain spectra. It means that inhomogeneous broadening is quite high, and we can use it to achieve broader spectrum. So varying the pump, we obtain, for example, higher bandwidths, and starting from 40 nanometers, we can optimizing the pump wavelengths, we can obtain 55 approximately nanometers bandwidth. But also we obtain the shift of the peak gain. So it means that if we need, for example, for certain application, some certain range for amplification, we can vary the pump wavelengths and tune the peak gain wavelengths. So it means that this strategy is good for increasing the bandwidth of our amplifier. So another possible strategy is to use 2 kinds of active centers. For example, here we use bismuth active centers associated with phosphorus and silica. And here you see that overlapping absorption spectra and distribution of these 2 kinds of centers along the preform, fiber preform. Another possible strategy is to use bismuth with some other element, for example, erbium, and here you see the measured gain spectra for bismuth, and the combination, simulation of combination of this kind of spectrum from bismuth with erbium doped one fiber. So it means that typically we can achieve more than 100 nanometers bandwidth in one fiber or maybe in two fiber connected in chain. What is published results for these several strategies? Here you see main results for combination of inhomogeneous broadening and pump radiation. The best results is shown here. So more than 140 nanometers bandwidth of amplification using two kind of active centers associated with phosphorus and with phosphorus and silica. And here you see that in this case we need to apply quite high pump power, about 3.45 watts. So from group from Southampton achieved similar results, but with a little bit smaller bandwidth, but they use only 0.8 watt of pump power, so it's much lower. And if we use only one pump wavelength, which is shown here, we can obtain more than 100 nanometers of bandwidth. So it's quite good results. Similar results for erbium plus bismuth. And here we can obtain more than 200 nanometers of bandwidth, which is very, very broad amplification spectrum. And finally, the group from Canada, which used our fiber, bismuth-doped fiber, in combination with erbium, obtain quite broad spectrum, about 100 nanometers in S-band. So it means that all the strategies can be applied, and if we consider all these possible variations, we can cover all this transparency window with only 3 amplifiers. So it's very, very good situation. So initially we have only 2 amplifiers, and we can cover only 80 nanometers. And now with 3 different compositions with different amplifiers, we can cover much larger region. So a couple of words about commercialization. So right now 2 companies
I'm afraid you should conclude.
Sorry?
You should conclude.
Okay. 2 companies offer 2 kind of bismuth-doped fiber amplifiers in O-band, so it means that now bismuth became commercially available. So probably I will say a few words just about core and cladding pumping. So initially we used only coarser pumping for bismuth-doped fiber lasers and amplifiers. But it's quite complex, you see, the scheme is quite complex. So we're starting from laser diodes and then converted to the core radiation using ytterbium and Raman lasers. Now we can use multi-mode laser diodes at shorter wavelengths, and we show that using specially designed fibers we can achieve bismuth-doped fiber lasers and amplifiers with not similar efficiency, of course, the efficiency is lower, but also still possible to get lasing and amplification. So this is conclusion of my talk. So now bismuth-doped fiber amplifiers became broadband and more attractive for practical application. 3 of bismuth-doped fiber amplifiers, 3 types, can now cover all telecom transparency window, which give more than 5 times increase in bandwidth. O-band VDFA is commercially available now, and cladding pumping is also an option for this type of lasers and amplifiers. Thank you for your attention.
Thank you. Unfortunately, you are out of time completely, so we don't have time for questions. We go to next talk, which comes from Mendeleev University from Moscow, Dr. Stopkin. direct laser writing of higher retardance structures in porous glass. Please keep on time. You have 15 minutes.
Good afternoon, dear colleagues. I am Semyon Stopkin from Mendeleev University of Chemical Technology of Russia, and let me present a presentation of the topic of direct laser writing of high retardance structures in nanoporous glass. My presentation is divided into 4 parts. Firstly, I will briefly tell about our motivation, especially laser writing of modifications in glass. Then the materials and methods will be discussed, and then the experimental results and conclusion will be presented. Recent progress in femtosecond lasers provided a high interest in the laser modification of transparent materials. It enabled by high intensity of femtosecond pulses that allows non-linear mechanism of energy absorption. So the flexible control of femtosecond laser expand the possibilities of such techniques as laser cutting, welding and drilling, microscopy, etc. So, and the laser beams with such polarizations as azimuthal and radial, and also optical vortices, are favorable for laser cutting because they enable better focusing. The conventional methods of fabrication of polarization converters that are used for converting initial linear or circular polarization of laser into radial or azimuthal are based on lithography, which is rather expensive, or based on liquid crystals, but it doesn't allow to produce optical elements with high optical breakdown threshold. So recently, a new technology that rapidly develops in the commercial field is laser modification of silicon glass and some multi-component glasses. Here you can see the several types of birefringent structures can be used in writing of polarization converters, and to date there are a few types of it known in silica glass. They are nanogratings, type X and type S structures. However, the nanogratings requires a lot of number of pulses and have high scattering losses. Type X structures are more transparent but still require a higher number of pulses. And the type S structures have the most high speed of writing, but both the type X and type S structures have low maximal retardance value that can be achieved. So the search for new materials for effective laser writing is still in progress. And recently it was shown that the formation of birefringent hollow cavities with only a few pulses as well as nanogratings is possible in nanoporous glass. So that's why we try to use nanoporous glass in our study for efficient writing of polarization converter. Nanoporous glass was synthesized from the commercially available sodium borosilicate glass of type DV1 that was thermally treated to induce two-phase liquation and then the resulting liquated phase was etched in acid solution. Chemically unstable phase is washed away, and the resulting nanoporous matrix consists almost entirely of silicon glass. The mean pore size of this matrix after removing a surface layer by grinding and polishing is 9 nanometers. Obtained samples of nanoporous glass have high transmission in a visible range. For inscription of birefringent structures, we used regenerative laser amplifier Ferros SP, working at a wavelength of 1030 nanometers. Energy of pulse was varied from 3 to 1000 nanojoules. Pulse duration was constant at 180 femtoseconds. Scaling speed was varied from 0.1 to 10 millimeters per second, and repetition rate was varied from 10 to 1000 kilohertz. Focusing was performed with low aperture 10 times magnification, a spheric lens with numerical aperture of 0.16. Retardance measurement was performed with optical polarizing microscope Olympus BX51. Two spectra was recorded for each birefringent structure in parallel and in cross polarizers oriented by 45 degrees relative to written structures. Then the normalized spectra in parallel polarizers were calculated by dividing intensity of light in parallel polarizers by the sum of intensities in parallel and cross polarizers. This normalized spectrum enables to estimate retardance value by fitting function. The dispersion of retardance was measured for structures with low retardance in visible and near infrared ranges, and it was found that the dispersion can be well described by linear function. And the retardance was determined with this dispersion at a wavelength of 633 nanometers. For comparison of nanoporous glass with silica glass, we inscribed at the same focusing conditions a row of birefringent squares in silica glass of KU1 type. The maximum retardance value for this row was 350 nanometers, and as you can see on the photo, these squares exhibit a high scattering losses. So we inscribed a series of birefringent squares in nanoporous glass. Here you can see different pulse repetition rates of 10 and 100 kilohertz. Pulse energy was varied from 3 to 1000 nanojoules in horizontal direction, and the scaling speed was varied from 0.1 to 10 millimeters per second in vertical direction. It should be noted that the most squares in cross polarizers have color appearance, which indicates of high retardance. At pulse repetition rates of 500 kilohertz and higher, range in which we can vary laser parameters that do not lead to the formation of these bubbles is quite narrow. So we limited pulse repetition rate to 200 kilohertz, and by investigating retardance of each square, we plotted pseudo-color maps. And as you can see, with the increase of pulse energy or with the lowering of scaling speed, the retardance value is rising. But some of the squares that are inscribed at high repetition rates or high pulse energies have inhomogeneous color appearance, as you can see here, for example. But it should be noted that the maximal retardance value we achieved was 1000 nanometers, which is record value to date for one-layer structures. To demonstrate the laser writing in nanoporous glass, we inscribed a polarization converter and described it with the helium-neon laser setup. The initial linearly polarized laser beam was successfully converted into donut-shaped form, which indicates that the first polarization of laser was linear, and after converter it became radial. It should be noted that the transmission of converter is virtually the same as the transmission of nanoporous glass itself, and the nanoporous glass has excellent transmission in the range above 600 nanometers, and in this case the transmission is about 68 or 86%. So, in conclusion, we studied laser writing of birefringent structures in nanoporous glass at low numerical aperture focusing conditions. The retardance up to 1000 nanometers can be achieved for single-layer birefringent structures in nanoporous glass. The polarization converter laser written in nanoporous glass and working at a wavelength of 633 nanometers is demonstrated, and nanoporous glass is shown to be a promising material for effective laser writing of birefringent phase optics and for photonics applications. Thank you for your attention.
Thank you so much. We have time for a couple of questions. Can you please go back to these multiple squares? You had some nice rainbow over here. Can you comment that?
What?
You have a kind of rainbow in the upper right and somewhere here. So this.
Why does it form?
Yeah.
We think that it is a stage of before the formation of these bubbles. So these inhomogeneities occurs as a pre-stage to this formation.
Some instabilities, you mean?
Excuse me?
Some instabilities, you mean?
Yes.
Okay. So, any more questions? Can you use mic, please?
You mentioned donut-shaped beam. Is it optical vortex?
Excuse me?
You mentioned donut-shaped beam.
It's not a vortex beam, it's a radially polarized beam.
So not optical vortex.
Not optical vortex.
Okay. So, if no more questions, let's thank speaker again, and we go to the last section, talk of this section. This is Dr. Ryachowski, sorry, from Fryazino. And Doctor, you have 15 minutes. Please keep in time.
Good afternoon, dear colleagues. The organizers made some mistakes in program, and the title of my work is Infrared Random Laser based on artificial relay fiber. This work was produced by Kotelnikov Institute of Radio Engineering and Electronics, and Prokhorov General Physics Institute of Russian Academy of Science. So first of all, I must discuss what my work was about. We will speak about what is a random laser, arrays of fiber break gratings as a cavity of compact random lasers, what experiment we done, and additional information. Principle of random generation. Conventional lasers consist of amplification medium and two mirrors. It's cause longitudinal modes, and in late 1966 it was proposed another laser generation with another type of mirror. This mirror in laser cavity can be changed by diffusion reflector. Such lasers have non-constant cavity length and cause lasers with incoherent feedback. Then in 19th, in St. Petersburg, Andrei Fotadi realized another type of laser application in optical fiber with Brilliant amplification. To produce such lasers in telecom fibers, such as SMF28, the length of fiber must be about 25 kilometers. So to make smaller fiber break gratings and lasers began to use fiber break gratings in optical fibers. The idea of producing compact fibers lasers is using higher reflection fiber break gratings. Such gratings inscribe in optical fibers with constant period. White light reflects from fiber break gratings, gets strong narrow band signal. In our institute, we have experimental setup where we can write fiber break gratings during our process. So the preform became to furnace. Then, after diametral control, we began to write fiber break gratings. To do it, we use XMR ultraviolet laser that works on wavelengths 2048 nanometers. After that, we focus by lens our ultraviolet signal to phase mask and route fiber break gratings. Then we coat our fiber by polymer coating and put it on a winding mechanism. The absorption of our fiber you can see on this slide. It's about 7 dBm on wavelengths 1535. On this, in this slide, present structure of array of fiber break gratings. Total cavity length is about 7 meter and consists of 700 fiber break gratings. Inscription consists of, is 43 dB In this slide presents a reflection spectrum of 7-meter cavity fiber. The total reflection of fiber breaks array about 0.7 at the wavelengths 1548 nanometers. The other words, the reflection is low. In this slide, you can see this scheme of our experiment. Here is our laser cavity. From laser diode, we came signal to our fiber, and after reflective, we became signal and get it to optical spectrum analyzer or optical power meter. The spectrum of laser generation shows in this slide. The lasing peak is located on the top of edge of spontaneous emission. Maximum efficiency of 15% at pumping 2050 milliwatt on 976 nanometers without high reflection of fiber break ratings at the end of fiber. In this slide showed power of output signal and an absorbed power. And the maximum laser efficiency reached 33%. Laser operate in continuous mode, time dependence on the laser output power, you can see on green line, and insert oscillograph trace, you can see on the red line. Average radio frequency spectrum you can see, and fitted by the Lorentz function line number 2. Self-heterogeneous technique with a delay line of 50 kilometers, the laser line width of 5050 gigahertz. And on this slide you can see our publication on this theme. If you had any question, I will ask you.
Thank you so much. We have time for maybe a couple of questions. Well, it seems to be too much clear to the audience what you've done. And what are the expected next steps? What do you think to do next?
The next step to do lonely fiber from 1 or 7 meters to 70 meters, and see what we shall have after that.
All right, interesting. Okay, thank you so much. And so I conclude this section and invite everybody to lunch.
Dear colleagues, let's start the next session of our conference. And the first talk in this section will be delivered by Dr. Mikhail Likhachev from Fiber Optics Research Center. Please.
Okay, thank you, Alexei. So the name of my talk is presented here. I'm from Diana Fiber Optic Research Center, which is now part of Prokhorov General Physical Institute. Here is the outline of my talk. So I will talk about two main applications for high peak power fiber lasers. First one is terbium doped fiber lasers, which are mainly for micromachining, and also for erbium doped fiber amplifier, which are typically used for LiDAR application. For both types, there are a lot of challenges which prevent achievement of high peak power in optical fiber amplifier, and I will discuss what they are, how to solve this problem, and what results was obtained. So first, terbium doped fiber lasers and micromachining. So micromachining is quite powerful tools. If you use picosecond or femtosecond radiation, the main advantage of this laser is absence of head affected zone. So you can see that mechanical cutting or cutting with CV laser results in a very bad quality of the cutting edge. And it is not so in the case of femtosecond laser. So you can drill holes with high quality, you can cut with high quality, and in general you can work with gentle material. Also you can work with such materials as glasses due to multi-photon absorption. So it's a very good technique. On the contrary to nanosecond lasers, there is no need in post-processing. Typically you can achieve, in the case of fiber lasers, high repetition rate, which is very important for increasing process of speed of processing. So for production, it's very important. So what is the problem with fiber lasers? The main problem is nonlinearity. So if you deal with high peak power, the fiber is the worst thing which you can choose to work with. The reason that you have a quite small core diameter, you have quite long length where light is propagated, and threshold of nonlinear effects is many order of magnitude smaller as compared to solid state lasers. Fortunately for fiber lasers, the benefits of it is possibility to operate at high average power, and it is the problem for solid state laser. So I guess now there is some type of competition between fiber lasers and solid state lasers for micromachining application. So one application have no problem with nonlinearity but have problem with high average power, and fiber lasers have problem with nonlinearity but it's good for high average power. So to win this competition, we need to increase mode field area and shorten fiber length, and I will discuss how it can be done, which way used now for this aim. The best results up to date was obtained in terms of peak power was obtained with photonic crystal fiber many years ago. So guys use photonic crystal fiber with very large core, it's around 100 micrometer, and they achieve at the output of their fiber peak power of around 1 megawatt, and after compression of 3 nanosecond pulses, the peak power was increased up to 4 gigawatt. Very remarkable result. The only problem that this is the rod type fiber. So this means that fiber with length of more than meter must be kept perfectly straight because it's very bend sensitive. Also, due to presence of hole, you cannot splice it with other fibers, so you need to use a lot of bulk optic to couple light in, to and decouple out amplified signal and so on. So if you see on the laser scheme, you will find that it's not a real fiber laser, it's now solid state laser, which is not, it's good for laboratory use, but for practice application it's a very bad laser design. So actually now a lot of efforts are spent for development of alternative fiber design, and a lot of such design was proposed by different groups. So it's leakage channel fiber, Chirley couplet core fiber, step index fiber which are not internally single mode, but where you can suppress higher modes by bending and so on. But to date, no results comparable with PCF was achieved using other large material fiber design, except one design. So this is tapered fiber. The idea of this fiber is very simple. So you have fiber, those core and cladding diameter continuously change along the length and can be increased maybe by 10 times. In this case, at the one end of the fiber, you have ordinary single mode core, so no higher mode propagates here. And if diameter change rather slowly, the fundamental mode during propagation along the fiber do not excite higher modes. So at the output of tapered fiber, you still can achieve a very high beam quality, so M square can be near unity, but you will have very large mode field area. And this technique allows to do many remarkable things, and many groups work with this type of fiber. It's a pleasure to say that in Russia there are two independent groups which develop such fibers, and one of this group is our group, and in particular we make a lot of efforts to optimize the tapered fiber design. So we work for core compound to make it with low numerical aperture to suppress photodarkening to increase ytterbium concentration in the core. So we develop technique for making fluorine doped cladding in our fiber, so the thick end can be just polished and it's very simple to use such fiber. So after all this optimization, fiber now commercially available, so it's quite simple in production, not very simple, but it can be produced in large number and can be used. So, and with this type of fiber we achieve a few good results. So I want to pay attention for these results, which was devoted to simultaneous achievement of a high peak and high average power in fiber lasers. So it is exactly what is necessary for micromachining. So you need to have pulses with high energy, and you need to high average power to increase speed. And it is exactly what we can demonstrate with tapered fiber. So we achieve more than 140 watt of average power. Peak power was nearly, it was sub megawatt. And we have very good beam quality, less than 1.2. So there is a dependence of beam quality on the signal power. And if we compare this result with those which can be achieved with PCF, we will find that average power in the case of PCF is lower. So the number is not differs too much, but here 130 watts it's a real limit, because transverse mode instability effect take place in photonic crystal fiber, and further increase of average power result in strong beam degradation. In our case, we were limited only by available pump power, and I'm quite sure that it can be 200 watts and more. Also, beam quality is worse in this case. So you can see that tapered fiber is really good design, and it should be used for development of high peak and high average power fiber lasers. The second thing which I want to talk about is erbium doped fiber amplifiers, mainly for LiDAR application. Of course, erbium doped fiber are much worse as compared to ytterbium in terms of efficiency, in terms of peak power, and so on. So you should have a very strong reason to use erbium doped fibers to develop high peak power lasers. And here are some reasons which might push you in this direction. So one of the advantages of of laser at this valence is eye safety. So damage threshold for human eyes for 1.5 micrometer is few orders in magnitude higher as compared to 1 micrometer. Also, you have very good atmosphere transparency and small benefits that you have a lot of available telecom components for this valence, which make developments a little bit cheaper. As a result, main application for such laser is remote sensing. So it's when you need to send some pulses into atmosphere, and you prefer to care that you do not damage anybody outside. There are a lot of different applications. So it starts from just ranging using light, and also there are some more complicated applications. I personally like these two. It's Doppler lidar. So when you do not only look for signal reflected from aerosol, you also check the wavelength shift due to Doppler effect, and in this case you can measure the wind speed. So it can be used in airport, for example, to make a wind map of 10 kilometers away from point when you put this lidar. Also, a quite nice application is measurements of CO2 concentration when you put two pulses, one inside the absorption band and another outside the absorption band, and compare its loss, and by this way also you can distantly measure concentration of CO2. So there is huge demand in high peak power lasers at 1.5. And let's see what we have. So there are three main schemes to build high power lasers at 1.55. One approach is well-known utilization of erbium and terbium fibers. It's have huge benefits due to high pump absorption due to ytterbium ions. But also it has strong problem like parasitic laser near 1 micrometer, and another problem is high numerical aperture of the core, which is necessary because you should dope it with phosphorus to organize good excitation transfer from ytterbium to erbium. Another approach is erbium doped fiber, just simple large material fibers, a single mode, which is pumped through the core. Typically, in this case, you need high power because large core fiber has, of course, large lasing threshold, and usual diodes have not enough power. So typically, it's pumped by Raman laser, and benefits its low quantum defect, high pump absorption. But disadvantage is low whole electro-optical efficiency of such pump source, and also it's quite complex and expensive laser scheme because you need to construct this laser. You must couple many watts of pump power with signal using a single mode WDM, which is not very simple to find. And third approach, which is mainly developed by our group, it's erbium doped fiber, which are erbium doped fiber without ytterbium, which are directly clad and pumped at 976 nanometer. So it's quite simple and cheap scheme because you just need fiber, pump combiner, and pump. But even after optimization of fiber design, it still have not very high efficiency and relatively long length, which is required to absorb the pump. I tried to summarize all the results of all the group on this graph. So it was done for only single frequency amplifiers. So that's why peak power here is not huge, because stimulated Brilliant scattering now limits the maximum peak power. But you can be sure that similar graph, but with a little bit different numbers can be made for femtosecond amplifiers or nanosecond amplifiers. So you can see that efficiency, pump-to-signal conversion efficiency can be very high if you work with continuous wave lasers. So now there are even reports with more than 50% efficiency. But it rapidly drops when you try to increase peak power in your amplifier. And when you reach some record value, the efficiency became very low. So this point was obtained by our group. So we set the record in terms of peak power, in terms of efficiency as compared to previous group. But despite it is the record value, it's still a very, very low efficiency, which is not good for practical use. So this is that thing which push us to think about novel amplifier design, and we found a quite good idea. So I will talk about this type of amplifier. So let's consider what is the reason for low efficiency when we work with high peak power. So this is image of our erbium doped fiber which pumped through the cladding. So you can see we have a very huge core. So it's 115 micrometer side of the square, so it's compatible with standard pump combiners, and 35 micrometer core. It's single mode, nearly single mode. So when we bend fiber, it's really single mode. So very good design. Many records was set with this fiber, but even at optimal length of 3 meter, we have a lot of unabsorbed pump power. More than 30% of pump is still unabsorbed. And this length we can achieve only 1 kilowatt peak power. If we want to get higher peak power, we should cut the fiber to shorter length, and in this case, more than 65% of pump is still unabsorbed, which of course is not very good for real amplifier. So we cannot shorten fiber length by cutting due to unabsorbed pump. Also, we cannot increase erbium concentration in the core because in this case we have cooperative up conversion, and efficiency also will decrease. So we'll have better pump absorption rate, but efficiency will be still low. In the case of erbium and terbium fiber, as I said, a separate problem is a huge core cladding numerical aperture. Actually, guys from Newfoundland make quite nice fiber design. It's fiber with pedestal, so they partially solve this problem. And their fiber was used in many works which set records for erbium and terbium fiber. But when we start test this fiber, we found one more remarkable thing. So if you use co-propagating pump and signal scheme, this fiber works with high efficiency only if very small gain is used with this fiber. So if you put input signal around few 100 milliwatts, you will achieve this value of signal with this value of pump. So it's around 20% efficiency. If you put a few watts of signal, you will obtain a much better result. But again, it's only 3 times 5 dB. It's not real amplifier. So it's also not very good. So actually we have 2 bad amplifiers of different design. One is erbium doped with good amplification but huge amount of unabsorbed pump, and erbium and terbium with good efficiency but very small gain. And idea was to combine these amplifiers. So if we put one fiber and splice it with another fiber, we'll can use a good signal from erbium doped fiber and unabsorbed pump to finally convert it into the signal into erbium and terbium fiber. So this scheme was realized. It's still very simple. So you have, instead of one, you just have 2 pieces of fiber, so erbium and erbium and terbium. But efficiency in this case became much higher. Of course, it's not still the record which you can see for continuous wave, but it's very good for high peak power amplifiers. Peak power is good. And now we are here. So it's all other groups, and this is our result. So it's a very good solution, and also if you deal with high peak power lasers at 1.55, I strongly recommend you to use it. And conclusion, so currently two rapidly developing applications are driving interest in high peak power fiber lasers. The first one is micromachining and another is LIDAR. So for micromachining, typically you use ytterbium doped fiber lasers, and we strongly suggest you to use tapered fiber in this case. And for LIDAR, typically you use something which is eye-safe, so erbium doped fiber amplifiers and preferably combined erbium terbium amplifiers must be used in this case. So thank you for your attention.
Thank you very much. Okay, we have time for a couple of questions, please. Yes, please.
You said that fiber from Newfern with pedestal has low efficiency or not efficiency. Maybe the gain should be very low to obtain good efficiency.
Yeah.
And what is the reason for that?
As far as I understand, when you have a high inversion, so you have something like up conversion in erbium terbium. So I guess excitation which you get from ytterbium ions drops electron from upper lasing level to even higher level. So this process is quite efficient, and you just lose a lot of pump photons if inversion is already high. So erbium ytterbium fiber works well only when inversion of erbium is low.
And what about concentration of erbium in this case?
I guess it's a maximum of all which I saw in erbium ytterbium fiber.
Any more questions? And regarding your tapered fibers, do they have some restriction on bending radius?
Typically, we do not recommend to bend it with diameter less than 18 centimeter. So if it's 18 or larger, it's okay.
Okay, fine. Thank you. Let's thank the speaker again. And we switch to next talk. Next talk will be delivered by Vladimir Kaminin from Prokhorov General Physics Institute. Please, your time.
Thank you for introduction. Hello, dear colleagues. Today I would like to present our work from the collective of authors from Diana Fiber Optic Research Center and Prokhorov General Physics Institute. We used here short cavity fiber lasers. So why do anyone need to use short cavity laser sources? Of course, we can use it in single frequency regime or high repetition rate regime. So in both cases, we can use such sources in scientific tasks such as spectroscopy, visualizations, interferometry, or high harmonic generation. In case of applied tasks, it can be reflectometry, medicine, metrology, or something like data processing or perspective communication systems. Of course, we can use such sources as master oscillators for high power amplifiers. What kind of active media should someone select to create such system? Of course, we can go to semiconductor or solid state solution. A lot of such solution already exists. But short cavity fiber lasers have strong advantages such as mechanical stability and resistance to damage from reflected or scattered radiation. For example, in our group, a lot of semiconductor lasers was damaged by during amplification. So what kind of fibers can be short active medium candidates. Of course, we can use standard silica-based optical fibers because low solubility of rare earth-doped elements. So we have to go to phosphate glasses, and there we can achieve more than 2–8% of ytterbium or erbium ions concentrations. At present moment, in several scientific groups have already realized some perspective fibers for 1 micrometer region ytterbium doped phosphate fibers with gain per unit more than 5.5 dB per centimeter. In case of 1.5 micrometer region, we can achieve from 3 to 5 dB per centimeter gain per unit. But if we'll take into account pure phosphate fiber, we have some problems such as difficult for fusion, poor mechanical strength, and poor air moisture stability. But in scientific groups, interesting results have been achieved. For example, Fabry-Perot laser with 100 milliwatts output power and distributed fiber or distributed feedback phosphate fiber lasers with low threshold was already realized. In case of mod-locked systems, one can achieve around 5 gigahertz repetition rate in 1 micrometer spectral region. But how can we improve such devices? How can we overcome restrictions such as mechanical instability or air moisture instability? In our institute and the Fiber Optic Research Center was proposed composite solution such as composite fiber. Such fiber can be made by rod and tube technique. Heavily phosphate rod can be placed in silica tube, then can be made perform, and then someone can draw the fiber and make laser. Here you can see first articles dedicated to this idea. Today I would like to say some words about a new generation of such fiber. Here you can see the core content and some characteristics. First of all, this fiber has relatively low background losses, about 2 dB per meter, and really high absorption at the 975 nanometer, more than 1000 dB per meter. So already our colleagues from Diana Fiber Optic Research Center have realized the nice result based on this fiber. It is a single frequency linear polarized laser. So here you can see the scheme. So they used just around 1 centimeter ytterbium fiber and Fabry-Perot resonator based on 2 fiber Bragg ratings. But fiber Bragg ratings was written not on the active fiber, but into the passive one. In this work, we tried to go further, and Bragg ratings were written directly into the active fiber. So this solution can be better because we don't have fusion splices inside the cavity, and we don't have additional losses. So this is the main scheme of our experiment. We have a short cavity that placed in thermal plate. We can change the temperature of the whole cavity. And the main thing is driver pump laser diode driver. We can change the regime of pump current from the continuous wave to modulated one, so we can change the regime of our laser from continuous wave to gain switch. To measure some characteristics, to provide good characterization, we used a lot of inconvenient methods, such as ring fiber interferometer, which can be some like scanning Fabry-Perot interferometer, but with inverse signal. And also we provide polarization analysis. We used just simple scheme, fiber polarization controller and fiber coupled isolator with phase axis blocked. At the output of this scheme, we can place a power meter or photodetector. So let's start from the first cavity. Here you can see the dependence output power on pump power. As you can see, it's very complicated and very interesting. Usually we can observe a linear one, but it is strongly non-linear. If we can also we can measure the spectral maps. This is a cross section is a spectrum depending on pump power. We can measure spectrum for every pump in this region, and then collect all spectrum into the one spectral map. So here you can see the spectral dynamics, also longitudinal mode dynamics, depending on pump power. For cases when we have one dominating longitudinal mode, we try to estimate bandwidth of it, and here you can see the oscilloscope trace at the output of our ring interferometer. So estimated bandwidth was about 2 megahertz. What about polarization? At the output of scheme that I mentioned before, we can achieve two different situations. One is almost sinusoidal signal on photodetector and almost continuous wave signal. Here you can see our interpretation of this process. In one case, we can set our polarization controller to provide transmission both polarization modes into the photodetector, and in another case when we suppress one of the polarization mode. In one case we can achieve a continuous wave signal, in another we can see polarization mode beating. Frequency of polarization mode beating was around 300 megahertz. Then we tried to thermally stabilize this cavity, but accidentally it was damaged and we can't continue. So we have to change the cavity to another one. Actually it was a little bit worse cavity than previous one, but we have a different temperature to measure characteristics. Here you can find the dependence output power versus pump power. As you can see, this dependence was complicated in all cases in the range of temperature from 60 to 24 degrees. In case of spectral maps, we actually have a lot of modes, so about 3 to 2 modes. And in case of one dominating mode, we try to estimate bandwidth. It was about 2.4 megahertz. So let's go to polarization. In case of polarization, we have a lot of modes. So on detector, it was really complicated dynamics, but the main bit frequency can be measured. It was around 293 megahertz, and we tried to change the cavity temperature and can shift bit frequency from 293 megahertz to 283 megahertz. So, as I mentioned before, our laser driver allowed us to modulate our pump current. So, as a result, we can obtain the output of our system as a single pulse, as a multi-pulse regime, or some relaxation oscillation mode. To obtain a single nice pulse, we should apply low current to our diode near the threshold of fiber laser. And then to achieve a nice pulse, we have to apply a rectangular pulse with duration in the range from 200 nanosecond to 20 microsecond. So here you can see the set of pulses achieved at the different pump pulses lengths. While we decreasing the pump pulse duration, output pulse of our generation are also decreases, and we achieve decrease from 150 to 95 nanosecond. Actually, on the top of the pulse, we still can observe bit frequencies. In case of shorter durations of pump pulse of our laser diode, some parasitic pulses can be observed. So such regime was unnecessary for some applications. We also decided to look at the stability of achieved regimes. Here you can see the set of distributions of our output pulses. Here you can see the amplitude around the main amplitude variation. So the relative standard deviation of the amplitude was around 6 to 8% for pulse durations from 6 to 20 microseconds. If we decrease pump pulse duration, the instability can increase. But in some cases, we can select some parameters that allow us to achieve higher stability, even up to 2.5%. So not only amplitude stability was investigated, we tried to measure some jitter parameters. In this case, we achieve, we can find the distribution of output pulse depending on pulse from generator. Here you can see that temporal jitter is about from 50 to 200 nanosecond, so it is comparable to own output pulse. However, at pump around 200 nanoseconds, the jitter can be decreased to 5 nanoseconds. but the generation mode has some parasitic pulses. So let me conclude. Spectral dynamics, language dynamics, and polarization composition dynamics of compact all-fiber lasers based on composite fibers has been investigated. We also investigated polarization beat modes. In all cases, it was around 300 megahertz. Also, we observe dependency beating frequency on the cavity temperature. And gain switching regime of short lasers was investigated. At present moment, output pulses with duration of less than 100 nanoseconds were obtained. But we suppose that we can shorten it in next generation of our cavities. That's all. Thank you for your attention.
Thank you for the talk. We have time for questions. Any questions? And when you investigated temperature stability of polarization mode beating, so what was the purpose of these measurements? So what is so important if you shift the frequency beating from 290 to 280?
Actually, it was interesting because in first cavity we achieved a nice sinusoidal signal directly from the optical system. If we can possibility to change it, it's interesting because slow tuning the 100 megahertz repetition rates sinusoidal signals, it can be useful for some kind of application.
Thank you. Any more questions, please?
Is your composite fiber single mode or not?
It was single mode. Yeah, because in previous experiments, already published experiment, it was single mode. It's the same fiber. In case of single mode.
Okay, thank you. Let's thank the speaker again. And we switch to the next talk, which will be delivered by Dr. Alexander Smirnov from Kotelnikov Institute of Radio Engineering and Electronics. Please.
Good afternoon, dear colleagues. Thank you for my presentation. And I'm pleased to present you today the result of our investigations devoted to the features of sign operation regime in moderately erbium-doped fiber lasers. First of all, I have to say a few words about motivation, about creation lasers based on erbium-doped fibers with moderately doped core. First is a wavelength of erbium fiber laser operation is 1.5 microns, which lies in the region of highest transparency of silica glass. And the second one is an opportunity to achieve a narrow, about several or sub-kilohertz operation bandwidth. So these advantages of erbium fiber lasers can be used in the such following technical areas, like as radiation sources for communication lines with ultra-high channel compaction, coherent lines of communication, coherent reflectometry, or low noise coherent source for sensing systems. Next is the opportunity of technology in our institute, Kotelnikov Institute of Radio Engineering and Electronics. It's the creation of all-fiber erbium lasers with a short cavity. For this purpose, in institute the technology of production of heavily and moderately erbium-doped fiber realized in Frязино branch of Institute, and also in our group have two technologies of production of erbium fiber cavities for lasers, is a point-by-point femtosecond inscribing technology and ultraviolet excimer inscribing technology by means of phase mask with fixed period of Bragg mirrors. And when we investigate such heavily and in this work moderately doped erbium fibers, we can achieve laser operation in both regimes, pulse or continuous wave. These regimes have investigated maybe 20 or 30 years, but some question till now haven't an answer. So the first question is the switching from pulse regime to continuous wave regime at room temperature. In the earlier works, we have demonstrated this switching by temperature decreasing to 77 kelvins. But in this work, we have used moderately doped fibers, and we show that this switching can be achieved at room temperature by increasing pump power. So you can see the absorption spectrum of our fiber with moderate concentration of erbium in core, with low level of clustering and low gray loss. So by red arrows demonstrated the wavelengths of laser operation. There is 4 lasers was fabricated, and there is an optical spectrum of these 4 lasers. Some of them was inscribed by UV ultraviolet technology. One of them was the shortest one was inscribed by femtosecond point-by-point technology and has the least efficiency, but with the least efficiency, it has a least bandwidth of laser radiation. And one fiber laser was inscribed by ultraviolet laser technology, but using the distributed fiber Bragg grating technology by special phase mask. We have shown 4 different lasers, but these 4 different erbium lasers have the similar behavior by with connecting of switching between pulse regime and Q-switch regime. And continuous wave regime. Firstly, we have measured, excuse me, this experimental scheme, but I think that this is maybe see one more time that have classical lasers with Bragg gratings inscribed at the edge of active fibers with lengths of 27, 60, and 170 millimeters, and one distributed fiber Bragg grating laser with 50 millimeters cavity. And using this experimental stub, we have measured efficiency by power meter, time specific features of generation and also radio frequency spectrum of generated laser signal. So the first is laser efficiency using the simple equation for laser efficiency. We can find the slope of all these efficiencies in the log scale format. We can see that the least efficiency has the shortest one resonator, but as I say above, it has the lowest line width of generation. So by the right panel we find alpha. It's obvious, it's equal to unity, and the second feature of these four lasers is the dependence of laser operation on pump power. At low pump power we have achieved Q-switch operation, and when we rise pump power, the laser operation switch to continuous wave regime, but with sign modulation. And we can see at these pictures at low pump power it's pulses with frequency and duration depending on pump power, and then achieve a CV continuous wave operation with sign modulation, but also we have investigate the frequency of this sign modulation. So what we have achieved during this experiment. So the same picture for four lasers we observed is the dependence of frequency of pulses or sign modulation depend on not pump power, depend on lasing power. So let's see the one because for this dependence are similar. There is three features. First is a slope beta equal to 0.4 for pulse regime. Then we have discovered the hopping of frequency when changing operation from pulse regime to continuous wave, and then slope of this dependence become 0.5 when laser operates in sine continuous wave regime. So first and the second features connects with the nature of pulse regime generation, and the third beta equals to 0.5 connects with the sine operation regime. From the theory, sine operation regime appears due to relaxation oscillation. At this slide, we can see at low power threshold regime when at the fixed pump power realized randomly, not stably, two regimes, Q-switch, it's blue line, and sine regime at red line. So we can see the hopping at frequency at the, and so we can see that at these two regimes with equal pump power, we have measured the equal lasing power in, for two types of generation. And the next is the dependencies of pulse duration and pulse amplitude dependence on lasing power. So by equals for for duration, third equation, and by amplitude of pulses, fourth equation, we can find from the experimental measurements slopes of these dependencies on also lasing power. And so these dependencies for all lasers is similar and about equals each other. And from this finding delta he and above finding beta, we can find the critical indexes equation for the lasing generation that experimentally was confirmed. So I have finished, and there presented the conclusions that I already say during my presentation. Thank you for your attention.
Thank you very much. Please, questions? Well, then I have a question. This sign operation regime, do you consider it as a drawback which should be eliminated?
As a what?
Drawback.
Drawback. We have found that in this regime, coefficient beta that we have found from experimental result that coincide with theory that consists of relaxation oscillation, and this parameter equal to 0.5 show us that the nature of this sign generation, sign operation is the relaxation oscillation.
I mean, in the beginning, in the motivation part of your talk, you said you list some applications, potential applications. How this sign regime could be applied?
I applied?
Yes. I mean, for applications, it looks like it's a drawback. It should be just CW, not sign. No?
I think that the erbium fiber laser operation, they almost already signed, but not everybody measures this sign oscillation in bioscillograms, maybe because of scale of oscilloscopes, or maybe resolution of oscilloscopes, maybe that.
So once again, what is the time period of these oscillations?
Time period, it's about hundreds, maybe. It depends on pump power and
order of magnitude. Order of magnitude.
It's about from 20 to maybe 1,000 kilohertz.
So, any more questions? Okay, let's thank the speaker again. Let's go to next talk. It will be delivered by Dr. Serafima Filatova from Prokhorov's General Physics Institute. Please.
Good afternoon, dear colleagues. Thanks for the introduction. My talk will be about obtaining of high repetition rates in holmium-doped fiber lasers. And this work was performed at the Prokhorov General Physics Institute in collaboration with Skolkovo Institute of Science and Technology and Russian Technological University. Ultrafast fiber lasers emitting in the 2 micrometer spectral range are in demand and actively studied because of their many possible applications, which you can see on the slide. And to improve the efficiency of such applications as material processing or advanced communication systems, the high repetition rates of ultra-short pulses are required. So the development and research of compact and stable laser systems generating high repetition rate ultra-short pulses in the 2 micrometers spectral range is an actual task. And holmium-doped silica-based fibers allow to obtain such a type of radiation at longer wavelengths compared to another fibers. And it should be noted that in addition to continuous sequences of high repetition rate ultra-short pulses, there is interest in bursts of high repetition rate ultra-short pulses for such applications as material processing and material removing. Let's briefly talk about passive methods of generation of high repetition rates. First of all, you can use short cavity. Such short cavity as the fundamental repetition rate will be initially high. For example, the cavity length of several centimeters and respectively repetition rate of gigahertz level. However, for silica-based fibers, there is a doping level limit to avoid clustering of active ions, and it is difficult to produce a short segment of silica-based fiber with high ions concentration. And in this case, another or hybrid glass matrices are being used. And the second method is frequency multipliers based on fiber couplers with coupling ratio 50-50 with delay line in one of channels. Here you can see such a chain of multipliers, and in this case you should expect a decrease of radiation intensity at the output of the system. And finally, the third one, and less technically challenging and more convenient, is the passive harmonic mode locking. It ensures the uniform distribution of multiple ultra-short pulses in the cavity under the high volumes of pump power. Passive harmonic mode locking can be explained by interaction of pulses via the acoustic wave effect and non-soliton component of radiation in the cavity, such as dispersive wave or continuous wave. And the advantage of harmonic mode locking is self-stabilization of repetition rate. And for holmium-doped fiber lasers, there is little information about harmonic mode locking. There is 2 works about passive harmonic mode locking in the literature. And the aim of our work was to investigate the effect of different mode locking methods in one cavity of holmium-doped fiber laser on harmonic mode locking obtaining. And here you can see the experimental laser model, which consists with a ring cavity, which consists of ytterbium fiber pump laser, 2 VDMs, WDMs, one for pumping, one for output of unabsorbed pump power, 2 polarization controllers, isolator, active holmium-doped fiber of 2 meters length, and coupler for output radiation. Here you can see the parameters of pump power and active fiber. We have studied 3 types of mode locking based on nonlinear polarization evolution, based on single-walled carbon nanotubes as central absorber, and hybrid mode locking combining these two previous methods. And here you can see parameters of carbon nanotubes. It was polymer-free carbon nanotubes. And this is a measurement setup and used equipment. Before the harmonic mod locking generation, we have investigated stability of laser operation, and first one was the laser-based mod-locked laser based on nonlinear polarization evolution. Here the experimental setup was a laser and cavity parameters and parameters of obtained radiation. So on the slide you can see a wavelength time dependence map for 1 hour, and you can see slight variations of wavelength during operation and signal to noise ratio and autocorrelation trace and pulse duration of 1 picosecond. During the experiments later we realized that we had to have to optimize our cavity, and we choose a better coupling ratio of coupler, and we changed the coupler in the cavity with coupling ratio of 1090, and we exclude 1 WDM to decrease cavity losses. And in such type of cavity, we obtained high repetition rates at increasing pump power. Here you can see the dependence of repetition rate and output power on pump power, and the maximum repetition rate was just under 600 megahertz. And in certain adjustments of polarization controllers and pump powers, we obtained burst of ultrashort pulses with varying quantity of pulses in the burst from 2 to 7, and with interval between pulses about 1 nanosecond. Next mod locking type was hybrid mod locking, that combining two types, nonlinear polarization evolution and single walled carbon nanotube. Here you can see the experimental setup, also parameters of cavity and parameters of obtained radiation. Also the wavelength time dependence map, and we believe that it shows less variations of wavelength compared to previous case, but signal to noise ratio and the pulse duration of 1.4 picosecond. Also, as for previous case, we have to also, as for previous case, we have to optimize the cavity, and we changed coupler with another coupling ratio and exclude WDM. And in this case, we obtained repetition rate of more than 600 megahertz. And here you can see also dependence of repetition rate and output power on the pump power, and output spectrum that corresponding to the maximum repetition rate, and also the autocorrelation trace and pulse duration of 1.8 picoseconds. And finally, the third type of mod locking, based on a saturable absorber, namely polymer-free single-walled carbon nanotubes. The characteristic of this, here you can see cavity and cavity parameters, parameters of obtained radiation, and the wavelength time dependence map shows more instability, as can be seen. Pulse duration of 1.3 picosecond. In this case, after optimization of cavity, after the changing of coupler and excluding WDM, we realized that for this type of mod locking, we could not obtain higher repetition rates. During the increasing of pump power, we observed transition from one wavelength generation to two wavelength generation, as can be seen here. And in the spectrum, we can see additional peaks, additional continuous wave components, maybe. We decided to change the coupler outputs, such as 90% radiation goes to the output and 10% stay in the cavity. And in this case, we could observe high repetition rates at increasing pump power, and we obtained about 160 megahertz. However, the spectrum also had CV components, CWV components, and on radio frequency spectrum, we observed different frequency components. So it was unstable, totally unstable regime. And to conclude, this slide presents some comparison with two other works, a comparison of our best case of harmonic mod locking with hybrid mod locking and with more than 600 megahertz repetition rate. In this work, the authors obtained 190 megahertz in the ring cavity, and mod locking was based on black phosphorus saturable absorber. And in this work, 570 megahertz was obtained, and the cavity was based on PM fiber, and the mod locking was based on the CSAM. We believe that our results are promising, and we will continue our investigation. And to this conclusion, I'll probably skip it, and thank you for your attention.
Thank you very much. Questions, please? So you have achieved repetition rates about 600 megahertz, and what prevents you to have even higher repetition rates?
Maybe we will continue to optimize the cavity construction.
So what would you expect your maximum possible value? There should be some mechanism that prevent you to go further.
As much as we can, I guess. We want to obtain about 1 gigahertz. I think it will be good.
10 gigahertz is possible?
I don't know.
Thank you. Any more questions?
Was there any jitter between pulses?
We did not investigate the jitter yet. But our aim of this work, I believe that we want to we want to apply such sources for material processing, and for this application, I think that there is not such not principle. Yes. 1G2. Yes.
More questions? Okay, thank you again. And we switch to the last talk in this session. This talk will be delivered by Andrei Zverev from Prokhorov's General Physics Institute.
Hello, colleagues. Very glad to see you all. My name is Andrei Zverev. I'm a postgraduate student at the General Physical Institute of Russian Academy of Science. Today I want to present you a work on the study of optimization of the length of cavity of erbium fiber lasers with a sub-gigahertz repetition rate of outshot pulses. The laser sources of outshot pulses with high repetition rate are widely used in various fields of science and technology. For example, they are used in high-resolution spectroscopy, optical communication, coherent tomography, or material processing. The aim of our works was a creation of erbium fiber lasers with a high fundamentation repetition rate of outshot pulses, investigation of its radiation characteristics, and optimization of the length of passive fiber in this cavity. And also suggest some methods for optimization for increasing repetition rate in the future. There are several methods to obtain high repetition rate of outshot pulses. Of these, the implementation of harmonic mud-locking regime or to creation sources with a short length of cavity with a high fundamental repetition rate of outshot pulses. First method has several drawbacks such as instability of generation modes or poor repeatability. When we are implementing a second approach, the difficulties arise. One of these is the length of active erbium fibers. Standard erbium fibers have a relatively low gain coefficient. Therefore, the length in the cavity reaches several meters, but do not make it possible to obtain main repetition rate of outshot pulse significantly higher than 100 MHz. To solve this problem, heavily doped fibers with phosphate core have recently begun to be used. The concentration of active erbium ions in these fibers in an order of magnitude than in the standard ones. But these fibers also has a drawbacks. They degrade in air and purely weld with standard optical components. Therefore, in our works, we used as an active medium a special composite erbium fibers with phosphate core and silicon clad. These fibers had the advantages of standard and phosphate erbium fibers. It's not degraded in air and is connected to standard optical components. At this slide, we can see a composition of core of these fibers, which ytterbium was added in composition for increasing absorption at the pump wavelength. The loss at 1.3 and 1.6 micrometers was 2 and 8 decibel per meters. and splicing loss with active fibers do not exceed 1 decibel. At this slide we can see our setup. As an active medium we used 12 centimeters of composite fibers. These fibers was pumped by laser jet on a 976 nanometers for a hybrid. Hybrid with one elements that play a role of valve division multiplexer, coupler and isolator. The coupling coefficient was 15%. The passive mud-locking mode was realized due present single-walled carbon nanotube placed between two FCPC pigtails. For ability to control the generation mode in this schema, this schema includes a polarization controller. In this case, we start from length of resonator. In this case, length of resonator was 1.9 meters. At the pump power of 300 milliwatts, we obtain a stable generation mode. In this case, the pulse repetition rate was 103 millihertz. Spectrum width and output power was 1 nanometer and 0.48 milliwatts respectively. I would to note that signal to noise ratio was more than 6 decibel with got good results. Next, we remove controller polarization and gradually reduce the length of the cavity. With the maximum shortening of length, we also obtain a stable generation mode of outshot pulses. In this case, less generated outshot pulses with a repetition rate of 298 millihertz. And in this case, the resonator length do not exceed 67 centimeters. At this slide, we can compare two obtained modes before and after shortening the length of cavity. As you can see, we significantly increase the repetition rate of outshot pulses to 300 megahertz, and do not, and in this case, the ratio of signal to noise do not being decreased. In second ways, we can see that there is a shifting of central wavelength nanometers, and output power was increased to 1.64 milliwatts. Also, I can add to what in both cases laser work very stability, and we observed self-starting of regimes. In the future, we planned to provide experiment with different length of active fibers. Also, we plan to reduce the length of a passive fiber by optimizing splicing and replacing of hybrid with optical division of with coupling 15% by hybrid with coupling of 5%, and we plan to use PM fibers, and we suggest was this help us to have a pulse repetition rate up to 500 megahertz. At this slide, we can see conclusions. In our work, we have created fiber ladders with main pulse repetition rate of 298 megahertz, which I think is mean information. That's all. Thank you for your attention.
Thank you. Questions, please.
Is your laser created fundamental repetition rate?
Yes.
A single pulse?
Yes, with a single pulse in resonator, because the length was 67 centimeters.
Any more questions?
Is there a way to reduce the length of components in your scheme, so to make higher repetition rate and shorter resonate?
Yes, but we have a problem with splicing because we have a long splice element.
You're satisfied? Okay. Any more questions? No. Let's thank the speaker again and all the speakers in this session. The session is over.
Микрофон будет включен.
Rahim. Раз. Рахим, здравствуйте. Вы можете что-нибудь сказать и показать?
Секции я первый.
Вас было слышно, можете повторить еще раз?
Я первый выступлю.
Нет, вы выступаете не первый.
Да, да. Слушаем меня?
Я вас сделал ведущим. Попробуйте с помощью плюсика загрузить презентацию. Плюсик в нижнем левом углу находится.
Да, я загружаю.
У вас все нормально со связью? Вы нас слышите хорошо?
Да, я слушаю вас.
Все отлично.
Немножко слабый.
Ну, конечно, с программой. Так, sorry, dear colleagues, my name is Bufetov Igor. I am from the Diana Fiber Research Center, and I will serve as a chairman at this session. Now we are starting, and the first talk will be given by Dr. Alagashev. Please. The talk title is Resonant Loss Reduction of High Order Modes in All Solid Band Gap Fibers.
One, two. Hello, everyone. I'm Alagashev Grigory, and today I will tell you about resonant loss reduction of high order modes in all solid band gap fibers. All solid band gap fibers is a type of microstructured fibers that consist of rods of high index high refractive index rods placed in a glass matrix. First experimental specimen of all solid band gap fibers was presented in 2004 by Russell and Knight and showed on this slide. It consists of a huge amount of rods placed in lattice. So this is based on idea that photonic crystal can confine light in a waveguide. On slide you can see, slide you can see transmission bands for this structure, and yes. First theoretical analysis of such fibers was conducted in 2002, and in this analysis you can see two types of fibers, is a single layered and three layered. There you can see losses of such fibers and smooth transmission bands. One can see that three-layered structure have only quantitative behavior, and you even don't need to place rods in a perfect circle to confine light. So earlier in our work we show that in model with 6 rods with such parameters that rods placed on a perfect circle with a radius of 12 micrometers and radius of 2 micrometers with a glass refractive index 1.45 and refractive index contrast of 0.05. We can see different behavior for transmission bands. Near 1 micrometer you see band with a lower loss with a resonant behavior, and near 1.5 micrometers you can see smooth band as was in earlier work, smooth bands. Also you can see that how fundamental mode in such fiber looks. And in this figure you can see resonant behavior if we change pitch of such structure. in about 12 micrometers, this is resonance. So if we add another row of rods in such waveguide, we see another resonance, but yes. And on the second figure, you can see another smooth band transmission and another resonant band. If we change not only pitch, but radius of the rod, we can see some kind of horseshoe dependence. So it's all resonantly low losses for fundamental mode. But our further analysis shows that not only for fundamental mode we can achieve such low loss, but for any other high order modes, such low losses can be achieved. So on this figure you can see two types of 6 rods waveguide and 9 rod waveguide. Why 9 rods? Because 7 and 8 rods waveguide show similar behavior as 6 rod waveguide. So we'll tell. This is fundamental mode losses from dependence from pitch for 6 rods waveguide. This is any other high order modes such as HE21, TM01, TE01, and you can see that dependence in this waveguide is flat. But when we have 9 rod waveguide, we see also fundamental mode resonance with small, the lowest in this case, losses. And we see that second order modes, such as HE21 and TM and TE modes have a similar resonance, but on another pitch. In case of 7 and 8 rods, behavior is similar to 6 rods waveguide. To further show that any other, in theoretical, any other modes can be any other modes can have such resonance, we take 12 rods waveguide, and we show region from 21 to 26 micrometers, and radius is 2 micrometers. We also see that this is fundamental mode, and this is TM01 mode, and red is HE21 and TE01 mode. It's also have a resonance. And I take only one, two of next order mode to show that it's also have a resonance, but TM01 have lowest possible losses in such fibers. In this figure, I show resonant loss reduction comparing with TM01 is the lowest possible losses for such pitch, and fundamental mode and third order mode. This is dependent from wavelengths, and you can see that behavior of dependence from waveguide wavelengths is similar. Yes. So is in this case, to show that is a similar mechanism of confinement, we can see on the power flow of such modes. This is a fundamental mode, and we can see some kind of vortex motion in the power flow, energy outflows and inflows to the core. So we can achieve low losses, low leakage losses. And similar behavior we can see on TM01 mode. It's in this you can see that power inflow through the rod and outflows between the rods. In case of third order mode, picture is similar but much more complex, and losses also is much more high. So in conclusion, I want to tell that for any other higher modes we can achieve low losses, and if we want to construct and we can construct a waveguide all solid bandgap waveguide for any in some region. Yes, we can construct waveguides that can confine light in a particular mode. Thank you.
We have time for a couple of questions.
I have two questions. First, is there any reason to make a low loss for higher loss? Typically, everybody tries to keep it high.
Maybe you want to get some new dispersive characteristics, and if you want, you can try to get it from high order mode. And sometimes you can try to use such waveguides, I don't know, to conduct vortices such as from HE to one modes, and maybe something more.
And in your case, the power will propagate both fundamental and one higher order mode, or it will propagate only higher order mode?
There's a region where we can, I think, theoretically take, I don't know, 1,000 much more loss for fundamental mode than for second order mode. So I think it's we can call it almost single mode, but for second order mode.
And the last question, is it sensitive dependent?
Of course, it's very sensitive dependent, and in case of experimental construction of such a fiber, these effects can be negligible. I mean, we even don't have resonance for higher order modes. it's very, you can see it's very sensitive to, I don't know, it's about percent, 100 nanometers.
I have a very small question. You have indicated delta n is equal 5 times to the 10 to the minus 2 power. Is it of importance the sign of this delta n?
Yes, yes, of course. It's
plus?
Yes, plus, yes. It works only for a positive refractive index contrast.
Last question, please. No. Let us thank the speaker again. The next invited talk will be given by Professor Romanov from the Saratov State University. Characteristics of mid-infrared light sources made of rare earth doped chalcogenide fibers on the base of model approach.
Thank you for introducing me. I am presenting here the results of one task of a joint project that we carry out with the Institute of High Purity Substances in Nizhny Novgorod. In this project, we developed an all-fiber optic platform for spectroscopic sensing in mid-IR, where vibrational spectra of various molecules of substances in gas, liquid, or solid phase are located. Development of such all-fiber optic sensors is important because they can be of low cost and size and open new possibilities for monitoring of environment in industries and in natural environment. Generally, such a sensor consists of a broadband source of mid-IR radiation, a sensor, a sensing element, and a recording system. A sensing element is a core-only fiber, and as a fiber is an open structure, radiation can penetrate into a surrounding medium, interact with the medium, and take information about chemical composition of this medium through the transmittance spectra. Here you can see this minima corresponds to vibrational transitions of molecules of the liquid, that is an analyte. Such all-fiber optic spectroscopic sensors will switch to higher level of monitoring in different areas, so they are of great demand now. Up to now, the mid-IR spectroscopy was developing over many decades. This is a well-known, reliable tool for chemical analysis of various substances. It was usually incorporated into FTIR spectrometers, and in particular, liquids were located in such very small volumes, thin cuvettes, because the absorption coefficient is very high. You can see here, this is large magnitudes of absorption. So the propagation distance was to be only several microns for recording such spectra. Such a spectroscopic system was developed in laboratories. In some recent years, fiber optic sensing elements were also incorporated into FTIRs with globars as a broadband sources of radiation, and this registration system in FTIRs. The sensing elements were in the form of direct fibers or curved or looped fibers. These are fiber probes that enable to achieve the detection limit of from 1 to 5% of concentration of an analyte, or with these curved fibers 0.1 to 0.5%. And results of these investigations were summarized in some papers starting from 90s of the past century. Here you can see more recent papers, and usually these liquid substances were aqueous solutions of simple chemical compositions like acetone, ethanol, isopropanol, and so on. Technology of the sensing elements fabrication has been developed, and here you can see examples of the fiber probes fabricated in the Institute of Chemistry of High Purity Substances. This is a bent probe, a loop probe, and this is a tapered fiber. And here you can see the absorption coefficient of the fibers fabricated in the institute and used for this probe's creation. With such a quite high level of the technology of the sensing probes fabrication, we still need to work with the broadband sources like glow bars, and continue the experiments with the FTIRs. I have taken only arbitrary some papers which demonstrate recent achievements in development of the fiber optics sources of broadband radiation. Generally, they developed in two directions. This is development of spectral supercontinuum and development of luminescence excitation in the rare earth-doped fibers. Today in the morning, we have heard very excellent results on development of the supercontinuum generation in microstructured fibers. There are also some works on the supercontinuum in step index fibers. And here you can see these papers from Russian and foreign scientists that demonstrate that this field is of great interest in developing now. So in my work, I am planning to focus on the luminescence excitation of the rare earth-doped fibers, and I'm planning to present some brief description of the modal approach that we have already used in design of the sensing elements. Then I will discuss the guiding properties of the rare earth-doped chalcogenide fiber of this composition doped with terbium. Then I will present some example of evaluation of amplitudes of the modes in the active fiber, and kinetics of terbium levels population and luminescence excitation will be considered through comparison of the model where we take into account spatial profile of the fiber modes and the fiber cross-section, and in comparison with the widely used 1D model. So I call this 1D model, and I will explain what does it mean. So model approach was very efficient in design of the sensing element because we were able to identify the condition for achieving high sensitivity of the sensing elements and to obtain a general understanding of their functionality. Here you can see in the picture, these are two modes. This is fundamental mode, and this is a higher order mode, and Here is magnified the range where they penetrate into the surrounding medium, and the higher mode is much more efficient than the fundamental mode. But anyway, for obtaining high sensitivity, we need to fit the length of the sensing element and a selective excitation of the high modes and so on. So now, in the wave optics theory, radiation propagation in a fiber is considered as a set of the guided fiber modes. Each of the modes is characterized by its special profile and a longitudinal propagation constant. Now we consider a rare earth-doped fiber and apply the model approach to such a fiber. So in particular, this is a fiber doped with terbium. The terbium has absorption bands in near IR that can be used for pumping, and also it has several emission lines for luminescence excitation. Terbium, a glass that was doped with terbium is of this composition. Generally, such fibers of such composition are very well presented in literature. That is why it was easy to work to find out the coefficients that are necessary for modeling. And it is surrounded by this glass of this composition, and the refractive indices were 1.55 for the coin, 1.35 for the cladding, and for the fiber radius, we state the value of 10 microns. Of course, the number of guided modes can be found by using this very well-known formula. And yes, this number is very large, it's more than 100. But what is practically realized? This is a question. What is realized depends significantly on the excitation, on light launching conditions. If a light beam is coaxial with a fiber axis, then only HE1M modes are excited, and these modes do not have internal caustics. To excite fibers with internal caustics, we need to shift or tilt an input light beam. But this is not good for any experiment. That is why we assume that the light beam is coaxial with the fiber axis, and then for these H1M guided modes, we have these numbers. For the pump of 2 microns 10, and for pumps of 3 microns only 7. So the number of such modes is not very large. Of course, I say about only one polarization. Generally, guided modes of a fiber are doubly generated in polarization. So if we take this into account, then we have 20 and 14. Now I provide an example on how to evaluate amplitudes of the guided mode in the fiber. This is a simple example when the light is launched into the rare earth-doped fiber with a single-mode silica fiber. Of course, this step-like discontinuity is one of the most difficult problems in electrodynamics. So rigorous solution is very complicated and needs great theoretical resources. But with this overlapping integral, we can approximately evaluate amplitudes in this fiber. And here you can see, I give here an example. I show the profiles, radial profiles of electric field for the silica fiber, this black line, and this is single mode of the silica fiber. And this is red line is for basic mode of the chalcogenide fiber. So they do not differ significantly, maybe only near the boundary of the coin cladding of the here in this range, because this is silica fiber is of different radius of 4.5 microns. And this high order mode, they have experienced such variations, and of course overlap integrals are of lower magnitudes. Here you can see these amplitudes, no amplitudes, but power of the modes. This is the power of the basic mode. It is close to unity. This is because this is good overlapping of these mode profiles. And the higher order modes, they are of this logarithmic scale. This is of 1 order or 2 orders less than the fundamental mode. But anyway, there is this is the second mode with m equal to 2. That is only 10 times less in power. And here we can see the higher order mode. So this result demonstrates that amplitudes of the mode significantly depend on the radius of the fiber and the pump wavelengths. So it's possible to manage amplitudes of the modes by variation these parameters. However, anyway, all modes have non-zero amplitudes. And maybe we can say about some modal noise. And now we consider kinetics of terbium levels population in the doped fiber. First, I will start with description of the 1D model. In this model, it was assumed that intensity did not vary in the fiber cross-section. So it was a constant magnitude. So then all these parameters are constant, and also populations of the terbium levels also do not vary in the fiber cross-section. In the 3D model that we are developing here, we can see that the profiles significantly depend on radial coordinate, and this approximation is quite rough. I believe that this approximation is good when we deal with a silica weakly guiding fiber, because this single mode is very smoothly developed over the fiber core, distributed over the fiber core, and in principle such an approach is feasible. But here in this high index fiber, this is not good. For solution of the system of kinetic equations, we used the parameters available in literature exactly for this composition and for the glasses doped with terbium. And here I present the results of calculation. This is variation of the ground level population. This is variation of the population in time and along the radial coordinate in accordance with the basic mode distribution. Here you can see that the population decays over much faster on the fiber axis than on the periphery. And here for the higher order mode, we have such a ring structure corresponding to this mode distribution, so that for this minima, the population decays slower than on the maxima. And here, these results are summarized as integrals over the fiber cross-section. So we can see the difference between the 1D model and 3D model. As a result, distribution of inversion population is also uneven over the fiber cross-section. Because of such uneven distribution of population inversion in the fiber cross-section, we have very special conditions for luminescence excitation. This problem was solved through the solution of these equations in 1D model and in 3D model. And here you can see that for pumping, we have a very different increase of population on the fiber axis because of the greater intensity of light beam here, and the profile of the mode also experience some change during the propagation. As a result, luminescence is excited in this model, and the maxima are not very different from the maxima provided by the 1D model, but the length of decay is much greater, and the fiber profile also experiences significant distortion. So, in the conclusion, we have demonstrated that if you take into account radial profile of a fiber mode, kinetics of levels population develops differently than in 1D model. So, in different radial points, develop differently in time. So, the population inversion accordingly is distributed unevenly over the fiber cross-section. And the pump radiation decreases in the Boss model, but the upper level is much more populated if we take into account the special distribution of the fiber modes. And what is, I think, very important is that the radial profile of a mode experience variation in propagation in such a medium where amplification is distributed unevenly. And as a result, there is some radiation leaking of some energy through the radiation field. So radiation field, this results in a permanent radiation loss along the fiber that sometimes is not taken into account. So thank you for your attention. Thank you.
Any questions?
The question about absolute power level in your estimations of model structure. You show which level of absolute level of power did you consider?
Mostly all the results were calculated for 100 milliwatts of input power.
It's enough for self-action.
Power. Yeah. Yes, for the a single mode laser.
Perhaps one more short question. One. No question. Let's thank the speaker again. And the next talk, Professor Skripachov from the Institute of Chemistry of High Purity Substances. Нижний Новгород.
Okay. Good evening, ladies and gentlemen. Today we talk about just a little about high purity chalk-designed glasses A5B6 as a material for mid-infrared fiber optics. That's outline of my communication. So we can see the chalk-designed glasses as optical materials for middle-infrared fiber optics. Chalk-designed glass fibers for modern applications. Main problem of the optical loss decrease in chalk-designed glasses and fibers, and some other problems. Okay. Among the non-oxide family of non-oxide inorganic glasses, special place has chalcogenide glasses. They are very perspective for mid-infrared from, for example, from 2 to 8 till to 11 micrometers. Okay. This general view of our fibers that was developed in the Institute of High Purity Substances, and of course in collaboration with Fiber Optic Research Center, named after Professor Academician Dianov. So you can see here that arsenic selenide fibers, arsenic sulfide fibers, this is initial preform, and this is part of Mendeleev table. The elements are suitable for preparation of chalcogenide glass. Okay, we did conventional step index fibers. Conventional step index fibers also we did PCF. That's our Brazilian developments. So the main technique was double crucible. Sometimes we use also rod and tube technique. Okay. I want to remember and to talk about our old developments and some application of our fibers. For example, this is fiber optic cable model for transmission of 5.5 laser radiation. We transmitted about 5 watts, but really now Japanese, they transmitted up to 100 watts. And this is a system for microsurgery. This is system of, for output radiation for spectrometer. And this is so-called fiber optic parameter that has 2 wavelengths. And this is regular optic cable for transmission of light image in to the matrix of microsensors. That was our developments in our institute together with the Fiber Optic Research Center. Okay. And I want to tell about more brand new developments, not in our institute, but all over the world. This is, for example, OTDM laser, OTDM channel. This is fiber optic couple for pumping of amplifier, and this is so-called Raman laser for about 400 micrometers. Okay. This is example of super continuum generation that our Brazilian developments. Really, it was not so large, but now the group of 7, they have now in arsenic selenide fiber still to 12 micrometers, 11 micrometers. So also it was made, we made so-called PCF, photonic crystal fibers, for shifting of 0 wavelength of dispersion, of chromatic dispersion. Also it was a so-called Mamoshev generator was done, model, based on chalcogenide glass, of course. Yes. So I want to say that chalcogenide glasses, fibers on their base are very perspective for some new modern applications, and they found some applications. Here our brand new development, it was maybe 2 years ago, made together with Moscow Physico-Technical Institute, so-called Martian DLS spectrometer, diode laser spectrometer for study of planet atmospheres. But the advantage of this apparatus is a low weight, so it's very good for some cosmic apparatus. That outline of application of ordinary step index fibers. We have so-called passive and active applications. No passive application for transmission of radiation, active application, for example, fiber lasers and some other sensors, harmonic generation. Okay. This is a possible application of infrared microstructural fibers, or so-called photonic crystal fibers. That's Zheltikov that outlined this. Okay, again, this is glass-forming compounds, and we have a lot of samples of glass. So we made fibers from sulfide glasses, selenide glasses, and doped by tellurides. So when we have selenide glasses doped by telluride, so we can broaden the diapason wavelength range. This is a basic thermal characteristic of chalcogenide glass. So you can see that TG, it is from 100 degrees to 620 degrees. But really, we're working with arsenic sulfide glasses and selenide glass. Okay. This is main scientific and technological problems arising at development of high purity chalcogenide glasses and low loss fibers in space. Of course, it's a difficult problem to prepare low loss fibers. So this is constituents of optical loss at light transmission through optical medium. Let's consider, for example, for arsenic sulfur glass. This is so-called electron absorption, this is multiphonon absorption, this is so-called weak absorption tail, and this is spectrum of our best fibers. And really, prediction, it is from 0.1 to 1 dB per kilometer, but nobody knows yet what the model is correct. So it is necessary to develop a model of optical loss. For selenide glasses, the curve the same, only it is shifted. It is shifted to slightly for 2 microns to this side, to more long wave side. For arsenic selenide, the same curve we have. Okay. The parameters that determine purity of chalcogenide glass and fibers of fiber optical loss. That, of course, first this is chemical purity of the glass. That a lot of constituents. Of course, existence of microcomponents with high volatility, homobonds and glass network. This is our new developments. We determined values of extinction, so-called extinction coefficients of impurities in chalcogenide glasses. And we can make conclusions that to achieve low loss, the impurity content it must be decreased to levels of ppb, so it's very difficult to obtain good glasses and fibers. Here you can see laser energy threshold for arsenic sulfide glass fiber as a function of submicron impurities content. So you can see the less quantity of microhomogeneities, the higher level of energy threshold. This is for YAG erbium laser, 2.94 micrometers. It's all about, I think, some megawatts in this. Okay. Here you can see the real content of impurities in the best samples of chalcogenide glasses. So we can make conclusions that we need to decrease this quantity about 1.5 or 2 orders of magnitude. Also, really, for example, arsenic sulfide glass, arsenic selenide glass, this is complicated. It has complicated structure in comparison to, for example, a silica glass. Really, this is so-called quasi multi-component glass. So sulfur as so-called homobonds, it has great influence for optical loss. It is necessary to take into account to decrease losses, not only impurities, but also we need to control the composition. This is our thermodynamic simulation of arsenic sulfide glass. So we can see that in the vicinity of stoichiometric composition, we have quite different composition for both sides. So it is necessary to take into account. Okay, this example of our best fiber, arsenic sulfide fiber. So 12 dB per kilometer, 3.5, and micrometers, and about 14 dB per kilometer, 5 microns. But really, this is 4.6. This is predicted level is 0.1, maybe 1 dB per kilometer. But really, we have now only this, but this bus. This is for I think for single mode fiber. We have about 100 dBkm, much higher. Here you can see comparison of optical fibers from chalcogenide glasses of various compositions. You can see that when we have more heavy components, acidic selenium, tellurium, it can go to 10 micrometers up to 11. Okay. And here the best optical loss all over the world. Really, this is for not for fiber. This is for we obtained for bulk material. But really, we have at 10.6 only about 3.5 dB per meter. Okay. This is dynamic of decrease of optical losses, and you can see that now we have like saturation, so very difficult to decrease. But we need to find the new ways of decrease of optical of impurities. Okay. This is further developments, further ways what we need to do. Okay. Now first, we need to find the new ways of purification and to take into account also composition of glass. Okay. Now. Okay. Thank you for attention.
Thank you. A couple of questions, maybe.
The question about the main reason for losses is impurity or crystalline phase in your material.
What impurity?
You talked about impurities and about crystalline phase in your glasses. Can you compare these two losses?
Sorry, я не понял вопрос.
Насколько я понял, это вопрос о том, как кристаллизация влияет на...
Crystallization? No, yes, of course. This is so-called phase purity. Yes.
I have a question.
Yeah, yes, of course. We need to take into account not only real impurities, but so-called, we need to provide so-called phase purity. The glass that will be free from crystals and like that.
Question, can you compare?
Can you compare?
What is the most important?
No, we can compare
Spectrum of losses.
Spectrum of, no.
You see,
Unfortunately, I did not take the spectrum, but really when we have crystallization, then we have about dB per meter. And when we have no crystallization, we have 0.1, 0, and less 0.4 dB per meter. So about 40 dB per kilometer. That strongly influence.
Other question? No.
Maybe I have a question.
And now we have online talk. Can we connect? Dr. Alekberov, do you hear us?
Я слушаю.
Oh.
Видите?
I see you on the screen. Perhaps.
Are you see?
Ага. Сейчас. Recent technologies are not yet perfect.
My name is Rahim. I study solids. I also greet all members of conference today. I would like to note that title of my report study of local structure and thermal properties, germanium, arsenic, selenium, sulfur, chalcogenate glass fiber optic materials. We know that chalcogenate glasses are effective optical photonic materials. These have interesting perspective, have wide transparent range, and low optical loss.
You hear us or not? Please answer.
The main purpose of article.
Please, do you hear us or not? Answer, please. Would you so kind? We don't see your presentation.
Do you see presentation?
No, we don't see your presentation.
Да. Do you see presentation?
No, not yet. Up to now, we see only the waiting screen.
Yeah.
Something goes wrong.
Do you see?
No. No, we don't see the presentation. Что-нибудь еще можно предпринять? Do you see the small white plus in the left corner of your screen? The technician says me that you can upload your presentation using this sign.
Left side.
In the left and down corner of the screen. Left down, plus white on the blue. Сейчас. No, up to now we don't see your presentation at all. I see demonstration of the screen finished, but nothing else.
This problem.
Dr. Alekberov, I am awfully sorry, but we cannot decide our technical problems. So we shall go further. Sorry once more. The next talk will be given by Yerushin from the Novosibirsk State University, nonlinear absorption and refraction study of quaternary barium chalcogenide formula crystal at around approximately 1 micrometer in nanosecond regime. Please.
Hello everyone, thank you to introduce. My team of work is study of nonlinear absorption and reflection of quaternary barium chalcogenide crystal at 1053 nanometers in a nanosecond regime. To date, the task of development of coherence radiation tunable in mid-infrared range is important because in this part of spectrum, contains the main windows of atmospheric transparency. There are a lot of characteristic absorption lines of vibrational rotational transition of various gases, and this area of transparency of many biological objects and semiconductor materials. Because of this, such sources can be used in atmospheric monitoring system, long-range optical communications, laser surgery, non-invasive medical diagnostics, and for many other applications. And one of the most efficient way to make tunable source in mid-infrared range is optical parametrical oscillators. So when we design high-power optical parametrical oscillators, need necessary to take into account nonlinear effects such as nonlinear absorption and nonlinear refractive. This work is devoted to experimental study of nonlinear optical characteristic of quaternary barium chalcogenide crystal by Z-scan technique. Today there are a lot of nonlinear crystals, but not all of these crystals can be used for pumping by neodymium laser, and not all of these crystals have necessary characteristics such as high laser damage threshold, some chemical characteristics, and etc. the most common oxide crystals can be used as for pumping by neodymium lasers, but they transparent only to 5 micrometers. And if we want to make source with larger wavelength, we should use other crystals. So you can see a few crystals on a slide and figure of merit of this crystal. The quaternary barium cognate have very high figure of merit, close to zinc germanium phosphide, and it's promising material for optical parametrical oscillator in mid-infrared range. So let's consider this crystal in more detail. Only in 2060 has been grown the crystal of sufficient size and optical quality. This crystal is an axial and belong to third class of symmetry. As you can see, the transmission spectrum of this crystal is transparent up to 18 microns, and the only current known components of nonlinearity tensor is almost 5 times higher than the largest component of already known BGSE crystal that make promising material for efficient parametrical Dunn conversion in mid-infrared range. And while study of laser-induced damage threshold, we observe decreasing of transparency of this crystal. So we start study this effect by Z-scan. The single beam Z-scan is a simple technique to determine the value of two-photon absorption and nonlinear refractive index of crystal. The principle is quite simple. The laser beam is focused on the sample to be moved along the optical axis, and the variable aperture is installed in front of detector. So the self-focusing and self-defocusing process occur by moving the sample, and the intensity of the incident radiation on the detector changes. Here presented the optical scheme for open and close aperture Z-scan. Neodymium ELF laser with at 1 micrometers and pulse duration of 5.3 nanometers and pulse repetition rate of 1 kilohertz was used as a radiation source. Faraday isolator was used to prevent back reflection into the laser, and half-life plate and polarizer was used to control the power. The sample was installed on a motorized linear transition stage, and data from open and close aperture were simultaneously measured by energy meters. To adjust the optical design, a polycrystalline plate of zinc selenide was chosen as a reference material. The plate had a minimal verge, and to prevent back reflection and the etalon effect, a single layer anti-reflection coating centered at 1 micrometers was applied to both faces. Here presented normalized transmittance at 200 megawatts per square centimeters. As you can see in the table, the nonlinear reflective index lies in the range 3.3 to 3.6 square centimeters per watt, which is good in agreement with literature data. So we start study the quaternary barium chalcogenate crystal for different polarization and intensity. BGG-SE plate also had minimal wedge and single layer anti-reflection coating at the both faces. Here presented two-photon absorption for extraordinary wave at different intensity, and here ordinary wave. And in the table presented measured two-photon absorption for both waves. The extraordinary wave has a high two-photon absorption due to lower band gap, thereby increasing probability of coincidence of the energy of two photons of incident radiation. And here presented the measurement of nonlinear refractive index of BGG-SE crystal for both waves. And you can see also the nonlinear refractive index for extraordinary wave higher than for ordinary wave, and increasing while we increase intensity. For the first time, the two-photon absorption and nonlinear refractive index were measurement at 1 micrometers, and the value of nonlinear refractive index are close to zinc tellure at 1 micrometers, which have similar band gap and two-photon absorption coefficient. Thank you for your attention.
Question, please.
Non-linearity was under your study, but the main value must be coefficient Gieper-Meyer. What is the value of coefficient Gieper-Meyer for your materials?
Repeat please, Hyper what?
Again, if you investigate by that scan, you must obtain the very important coefficient, Gieper-Meyer value. How much is it?
Не совсем понял. Какой коэффициент вы имеете в виду?
Для того, чтобы оценить вашу нелинейность, вам нужно показать, каковы коэффициенты Гieper-Meyer. Правильно?
Нет.
Нет?
Нет. Я первый раз, знаешь, слышу, если честно.
Но почему? Это же общее.
Here you can see the formula of the scan, and here we have only intensity and length of our sample, and of course linear absorption.
Perhaps later. Next question.
You used 5 kilohertz repetition rate for that scan measurement. 5 kilohertz repetition.
1 kilohertz.
1 kilohertz.
1 kilohertz.
Okay. In that case, you have a thermal effect.
Yeah.
And the question: did you separate thermal effect and electronic nonlinearity? For that scan, it's not so easy.
Yeah.
You can have absolutely different formula for that scan estimation for thermal that scan and thermal avoid effect.
Yeah, thermal effect. We don't separate them, and as you can see, it's increase while we increase the intensity, and it's increased because local heating. It's occur local heating and decrease the band gap. So, yeah.
Other questions?
Should separate.
No.
So, how can you prove that your results are correct? So, did you use an etalon maybe, or there are also some formulas developed by Sheikh Baha for spectral dependencies?
Yeah.
Maybe did you use them for comparison?
We take already known zinc selenite crystals, and we compare with Sheikh Baha'i. So it's good agreement with literature data. Yeah.
Any other question? What's enough? Let's thank the speaker again. And the last talk of our session will be rather intriguing name, Gyrotron's Impossible is Nothing. So, Dr. Sobolev.
Hello, I present the results and advances of a big team from Institute of Applied Physics and JICOM from Nizhny Novgorod, Russia, regarding the sources of high power sub-terahertz and terahertz radiation called gyrotrons. So on this diagram we can see that gyrotrons are on the high power side of the sub-terahertz spectrum, and this maybe now we can talk about the terahertz, maybe one or more terahertz, and the power of gyrotrons is up to megawatts in continuous wave, so this is quite a modest picture. And gyrotron uses microwave and free electron interaction in circular, mainly circular cavity. On the diagram, the gyrotron radiation is here, and it can produce higher power due to interaction with high order modes. For example, if we can use TO2 mode for several kilowatts or tens of kilowatts, and for relatively big wavelengths. But for several hundred kilowatts or up to megawatts radiation, we can use high order modes with wave numbers several tens. So the main usage of such powerful devices up to now were plasma facilities for energy fusion technologies, for example, ITER, and for multi high charge ion sources and several other applications. And our gyrotrons will work in ITER. 4 gyrotrons are already delivered, and 3 more gyrotrons were produced. Of 8 gyrotrons which should be delivered by JICOM. So these gyrotrons produce 1 megawatt of continuous wave power for frequency 170 gigahertz, and such powerful devices can be made even more powerful if the parameters are tuned. We can reach higher efficiency and higher power. And now we are trying to get higher frequencies from the same type of resonator. It's maybe not very easy, because the tolerances tend to be more tight, and the size of the resonator should vary not more than by Y micrometer, and with advances in calculation methods of output optics and windows, we can produce sources which will work on 2 or more frequencies with high power and high efficiency output. This would be needed for future generations of fusion facilities, and the maybe more interesting from the theoretical point of view is the way of producing coherent radiation from multiple sources, which would allow us to infinitely, up to budget, increase the power of coherent radiation. With advanced optics, we can enter the radiation into the resonator, and the output radiation will leave the generator volume in another way, and only several percent of input radiation allows one to make the output radiation coherent with the input radiation. Keep it up to a level that we can combine the radiation from several sources into one beam. Or if it's not needed, we can make a phased array of megawatt sources. So these experiments were done this year. We used the 10 kilowatt input driver gyrotron, which was used to power up the 1 megawatt gyrotron. We were limited by our test facility because facility in Institute of Applied Physics allows one only to use pulses up to half of millisecond. So on the side we can see that the frequency can be set by the input gyrotron, and the input gyrotron can be stabilized by external clock up to the tolerance of the external clock. So we can completely steer our frequency and even phase. So here we have the width of the frequency band approximately 20 kilohertz because we were limited by half 50 millisecond. So if we will go to continuous wave, we can reach the frequency width of 1 hertz if our external clock allows us. So this is a scheme of experiment. This is a driver gyrotron. This is a transmission line which converts polarization and mode, and on the other side we have a 1 megawatt gyrotron. As for driver gyrotron to meet tight tolerances, we can use a series of resonators made and tested on our test gyrotron setup, and then we can use the resonator which exactly fits our frequency. And the driving the gyrotron by external source also allows us to reach higher power by less current, so to increase efficiency too. The other type of improvement which we could use on our gyrotrons is the use of significantly different frequencies, for example, for use on high power spherical tokamaks, and here are the calculation results of first harmonic and second harmonic, which shows quite good efficiency because it suits spherical tokamaks, because its magnetic field significantly differs from the inner side to outer side, and we have to use very different frequencies for heating plasma in inner areas and in our outer areas. So for such tokamaks we can use the gyrotrons which can be used on first and second harmonic with close power and efficiency. And as for higher frequencies, we gained the half terahertz radiation of continuous power of 200 up to 250 watts, and we can reach even terahertz frequency due to very good maybe properties of mode numbers, because Bessel numbers, Bessel function roots offers us the possibility to generate fifth harmonic of radiation with quite good efficiency. So we already got the continuous wave of 1.25 terahertz, and for existing gyrotrons we can use this offers new possibilities in spectroscopy applications, and maybe for cancer treatment, because it was found that cancer DNA have peaks in 1 to 2 terahertz frequency band. And as for the last application, which is maybe not in near future, but the use of phased array of powerful gyrotrons can allow us to even launch rockets. We can use 1,000 of 100 gyrotrons to even launch satellites with quite considerable weight, and first experiments of course are made on single gyrotron, but it was shown that we theoretically can even go to space with our powerful sub-terahertz and terahertz sources. Thank you for your attention.
It's clear that a lot of things are impossible. A lot of things are possible. In your case, what is possible or what is impossible?
In near future, it is possible to reach up to 2 terahertz of several watts of continuous wave radiation with single gyatron and as much power as you want, limited only budget with coherent sources fed by single gyatron.
There is a bird between possible and impossible.
For now, it's 2 terahertz. It's not a wall because we can reach maybe high frequencies on first harmonic, and this would allow us, of course, to produce maybe up to 4 or 5 terahertz on fifth harmonic.
Okay, next question, please. It's difficult to have a question to large installations, high powers, and so on. Well, let's thank the speaker again. And we have now the possibility to make another attempt to hear a talk, the first talk of our session. Let's make a try. Okay. Next, now we try to hear the talk from Baku. Can you connect us? It's Dr. Alikberov, do you hear us?
Yes.
No. Yes?
I'm ready.
Can you see? I don't hear.
For technical problems, I would like to note that title of my report is Study of Local Structure and Thermal Properties in Germanium Arsenic Selenium Sulfur Chalcogranite Glass Fiber Optic Materials. The main purpose of this article is study relations between the parameters of local structure and glass transitions in germanium arsenic selenium chalcogranite glass systems. For this purpose, energy dispersive X-ray analyze X-ray diffraction and differential scanning calorimetry experiments were performed, and theory of topological constraints, chemical ordered network models, and idea of layered glass structure were applied. Another experiment is glass composition were synthesized. The molar percentage of elements in studied composition had been determined by energy dispersive spectrometry, and this result as described in Fig 1. The results shown confirm the synthesized class composition with error plus minus 0.04 and 0.2, and also consistent with other compositions. The result of X-ray diffraction experiment to determine the structure of studied materials are presented in Figure 2. Amorphous of materials was proved by Watt maximum in X-ray diffraction. Fig shows that the first sharp diffraction peak is observed in all composition. Values scattering vector varies in range of 0.99, 1.41. FCDP in X-ray diffraction was explained with the presence of medium range order in amorphous materials with covalent bonds. By using, we calculate dimension of parameters S0 and M0, short range order, medium range order from these formulas. This is as described in table 1. From these results, clear that composition with relatively high topological regularity have high dimensional short range, odd, and medium range. Or for analyze glass transition problems in this composition, differential scanning calorimetry result was described in Fig 3. Note that these experiments have been performed on Colin rates and Hayton rates 25. The transition temperature for all composition was determined from DCG, Colin, and Hayton curves. We also calculate empirical TG values, average bond energy, are parameter using Boolean formulas. We can see from the table 2 agreement is particle good between experimental and values of glass transition temperature calculated from formula and 1 and 2. Note that in formula 2, yes, belong belong to contribution arising from strong bonds, but second term of equation denotes contribution arising from weaker ones remain after strong bonds have been maximized. And also that average bond energy is calculated according to chemical order network, and obtained result are described table 2. Where formula 4 is that atomic fraction of chalcogenic, X and Y are atomic fraction non-chalcogenic. Another that analyzed scientific research shows that our parameter allows to determine presence of chemical threshold and in binary and multi-component chalcogenic glasses, and allow to determine correlation between glass transition temperature in composition. Finally, all mentioned results are described table 2 and 3. Mainly to theoretical models applied for explain experimental result and calculation described in tables. theory of topological constraints proposed by Professor Phillips Antwerpe, an ideal layered structure proposed by Professor Tanaka. By applying theory of topological constraints, obtained results are described in Table 4. When average coordination number is equal 2.4, then share of zero frequency oscillation modes condition is satisfied. According to topological constraint theory, this condition represents the most stable glass state. In this case, the difference between the transition temperature, this crystallization temperature of glass composition should be greater. However, if we compare the result obtained in Table 2, Table 3, and 4, becomes clear that composition of this, which formally satisfied condition 2.4, and F is equal 0, but does not actually represent composition corresponding to most stable glass state. As can be seen from these tables, empirical and experimental values of glass transition temperature correspond to composition as well as value of average bond energy are not maximal. On the contrary, other glass composition are more stable, and difference between glass crystal transition temperature and average bond energy is greater. To solve these problems or contradictions and to calculate among topological constraints, a new formula idea layered structure was proposed by Professor Tanaka. These results are described in Table 5. In Table 5. We can see, according to layered structure approach, highest temperature difference between the glass transition and crystallization temperature in this topological regularity composition. These results are associated with composition being closer to both chemical and topological ordered composition. Finally, I would like to note that several important results have been obtained from Table 1, 2, 3, 4, 5. This result. By applying theory, topological constraints, and chemical ordered network models, and also applies layered structure, it has been determined these compositions are more stable classes. This result is related to larger difference between the glass transition crystallization temperature, glass crystallization temperature, and as well as high topological and chemical ordering studies composition. According to layered structure approach, the highest temperature difference in studied composition associated with composition with closer chemical and topological order. It can be concluded that Tanaka's approach layered structure is more consistent with both result of chemical ordered network model and experiment results. Relatively high value of short range and medium range order parameters of local structure in glass composition satisfying the mentioned condition affect glass transition temperature in case it values to increase. There is a comparative analysis of X-ray diffraction and differential scanning calorimetry curves. It has been determined there is correlation between glass transition temperature with short range and medium range order parameters of local structure. For attention, thank you.
Huh? Do you hear me, Rahim? Do you hear me now?
Please repeat question. Please repeat the question.
Do you hear me now?
I have finished report.
I believe in such a case it is difficult to ask questions. We thank you once more for your talk. Thank you, Rahim. So this session is out. Thank you very much.
Up to the sight of neon lights flashing outside my window. It's 5 a.m. I still can't get you off my mind. Distant sounds fill my head. I spend days walking the streets trying to find you. Watching the people around me. Have I seen her before? Anything I've seen. If I could just recall. Is it just a dream? Have I seen her before? If I could just recall. Distant sounds fill my head. I spend days walking the streets trying to find you. Watching the people around me. You're not there. Have I seen her before? Anything I've seen. If I could just recall. Is it just a dream? Have I seen her before? I keep having these strange dreams. I'm holding your hand, just as I'm about to tell you how I feel. The dream suddenly ends. Anything I've seen. Is it just a dream?
Get the glory. 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 Get the glow. Get the glow. Get the glow.